Hello there and welcome to Science for Sleep, where curiosity settles into a comfortable chair and the vastness of the universe becomes something you can explore without needing to stay wide awake through every detail. Tonight we're drifting towards something enormous, something so vast that even the word enormous feels a little shy trying to describe it. We're going to spend some quiet time with IC 1101, a galaxy so large and so hungry that calling it impressive barely does it justice. It is one of the biggest galaxies we have ever discovered, one that has grown not by accident but by gently pulling in and consuming others, a kind of cosmic collector shaped by eons of collisions. As you settle in, let yourself imagine the quiet distance between the stars, the steady glow of old starlight, and the slow turning of structures far older than any world we know. Before we wander deeper into this part of the universe, I'd love to know something simple. Where are you listening from tonight? And what time is it for you in this small moment of your own life? The contrast is always beautiful, isn't it? Here you are, wherever you happen to be, maybe with a pillow tucked just right, or a blanket pulled to your chin, and out there in the deep reaches of space sits a galaxy millions of light years wide, glowing faintly in a place almost no one will ever travel to. Yet in this moment, your thoughts are close enough to touch it. If you find this journey gentle or soothing or simply a pleasant way to ease your mind toward rest, it would mean a great deal if you would give the video a like or perhaps subscribe. It helps this quiet corner of science float just a little farther, reaching more people who might need a calm voice to soften the day. Now, make yourself comfortable. Let the stillness around you settle into something steady and familiar. We're heading out far, far beyond the cozy light of the Milky Way. Somewhere in that distant region of space, sitting like a monarch among smaller companions, is IC 1101. To picture this object, you need to take whatever sense you have of galaxy size and stretch it, not dramatically or theatrically, but slowly, as if someone were rolling out dough with a patient, careful hand. IC 1101 isn't just big, it's enormous in a way that challenges what we normally imagine when we think of galaxies. The Milky Way is already huge, a graceful spiral of hundreds of billions of stars, wide enough that a beam of light, the fastest thing we know, would take around 100,000 years to cross from one end to the other. That's already beyond anything we deal with in everyday life. But compared with IC 1101, our home feels almost modest. IC 1101 is located at the centre of a galaxy cluster called Able 2029, about 1 billion light-years from Earth. Even saying 1 billion light-years doesn't quite settle in, because our brains don't really have a drawer to put that kind of distance in. If you could somehow travel at the speed of a light, that impossible speed where time itself begins to behave strangely, you would still need 1 billion years to get there. That's older than most stars you can see in the night sky. When you arrive, you'd find a single galaxy so spread out that the Milky Way could fit inside it several times over, almost like a pebble inside a cathedral. IC 1101 stretches roughly 6 million light-years from end to end. It's not a tidy spiral or a delicate barred structure. It's more like a swollen, elongated cloud of stars, glowing faintly in golden hues because its stars are old, very old. The reason it's grown to such an astonishing size is not simply that it formed that way. Instead, IC 1101 grew by drawing in other galaxies over billions of years. As the central galaxy in its cluster, it sits in a gravitational position of authority, if you could call it that. Everything around it feels its pull. Smaller galaxies orbiting in the cluster move along trajectories that eventually bring them too close, and when they do, they're absorbed. Not quickly, not violently, not in a dramatic burst of chaos, but in a long, slow process where stars drift and mingle, where the shapes of galaxies blur and dissolve, and where the light from entire systems becomes part of a bigger whole. Each merger adds more stars, more dust, more mass. Over time, IC 1101 has become something that almost seems impossible, a record of billions of years of consumption, with the quiet patience of something that has nothing but time. What makes this process interesting is how gentle it usually is. When we imagine galaxies merging, it's tempting to think of explosions and turmoil, but stars inside galaxies are so spread out that direct collisions are rare. When two galaxies come together, their stars mostly pass by one another like two crowds, slowly merging in a giant open square. Gravity twists their paths, bends them gently, draws them into new orbits, but the stars themselves continue on mostly unchanged. The real drama happens in the vast clouds of gas and dust between them, which can spark waves of star formation or be stripped away entirely. Over billions of years after each merger, the result becomes smoother and rounder, with any traces of the original shapes fading into the uniform glow of an elliptical galaxy. IC1107 is one of the largest examples of this smoothing process, a kind of cosmic memory foam that has absorbed more stories than we can count. As we move closer in thought, imagine what it might feel like to drift through one of its outer regions. You wouldn't see bright clusters or tight spiral arms. Instead, you'd be surrounded by an immense thickness of old stars, spread far apart but shining in a soft collective glow. Many of those stars are red or yellow, aged and calm, long past the turbulent youth that fills younger galaxies with bright blue starlight. Because of that, IC1101 has a warm, mellow colour. Even from afar, telescopes catch the hint of that older light, almost like a faint tint of amber. This gentle coloration is one of the signs that IC1101 hasn't formed many new stars in a very long time. Most of its raw materials for star formation have likely been used up in earlier mergers or stripped away into the surrounding cluster environment. The core of IC1101 is expected to be incredibly dense. Most giant elliptical galaxies host enormous supermassive black holes at their centres, far bigger than the one in the Milky Way. Our own black hole, Sagittarius Aorist, has a mass of about 4 million suns, but in galaxies like IC1101, those central black holes can be thousands of times more massive. The gravitational influence of something that dense extends across vast distances, shaping the orbits of stars and influencing how gas moves within the inner regions. We don't have a direct measurement of IC1101's central black hole yet, but based on similar galaxies, astronomers expect it to be staggeringly large, possibly one of the most massive black holes in the observable universe. Imagine something so heavy that even light itself cannot leave its edge, yet it sits calmly within the glow of a galaxy millions of light years wide, quietly controlling the motion of billions of stars. As we drift farther in thought, consider how long this galaxy has been growing. When the first proto-galaxies were forming in the early universe, IC1101's ancestors were likely already beginning to gather material. Over time, as clusters formed and grew, the galaxies at their centres naturally became the largest, simply because they had the most opportunities to merge with others. Every orbiting member of the cluster was slowly influenced by the gravity of the central region. Some galaxies took billions of years to spiral inward, gliding along slow, curved paths that eventually brought them into IC1101's reach. With each merger, the galaxy's shape changed slightly, but because these events happened so many times, the result became almost perfectly smooth. No spiral arms, no sharp features, just a soft, rounded glow. This process isn't finished. Even now, if we could see IC1101 clearly, we would likely find faint streams of stars around it, long trails of light left over from galaxies that are still in the process of merging. Some of these streams may stretch hundreds of thousands of light years across, barely visible, but full of clues about the galaxies that once existed. If you followed one of those star streams, you'd travel through long, quiet regions where stars drift peacefully, sometimes alone for unimaginable stretches of distance. Space inside a galaxy is mostly empty, even in something as enormous as IC1101. You could travel for years at high speed and never get close to any star. Yet the combined light of all these distant stars creates the soft glow we see from far away. And somewhere in that vastness, there are smaller galaxies still slowly making their way inward, destined eventually to join the mass of the giant at the centre of the cluster. Nothing in a galaxy cluster remains untouched by the gravitational pull of the central galaxy forever. Over long stretches of time, everything drifts, everything moves, everything adjusts to the invisible pulls and pushes of gravity. In that sense, IC 1101 is like a slow, steady sink in the middle of a cosmic landscape. Not a violent one, not a sudden one, but a patient one that has gathered the light of countless galaxies and will continue to do so long after our own era has passed. As we stay with this image, letting the scale of it settle gently into place, it becomes easier to understand why astronomers find galaxies like AC 1101 so intriguing. They're not just large, they're records of cosmic history, every merger preserved in their shape, every orbit slowed by their gravity, every trace of star that once belonged to something smaller, now drifting quietly within a much larger home. These galaxies have experienced the universe not in fast bursts or sudden leaps, but in an unbroken sequence of events unfolding over billions upon billions of years. And in that sense, drifting through the idea of IC 1101 is almost like watching the slow turning of a page that has been written over countless times, each new line blending into the next with a kind of steady continuity that encourages us to keep exploring what lies ahead without needing to rush or conclude anything yet. When you first encounter IC 1101, even in thought rather than sight, there's a sense that your usual sense of size becomes a little unsteady. It's not that the galaxy is dramatic in shape or vibrant in colour, because it isn't. In many ways, it looks simple. A faintly glowing oval of older stars, hazy around the edges where its outer regions start to blend with the darkness of the cluster around it. But when astronomers measure it, or when you picture its scale carefully instead of quickly, the numbers begin to stretch far beyond anything familiar. Meeting IC 1101 for the first time is a little like trying to grasp the idea of an ocean when you've only ever stood beside a pond. You think you understand what large means, and then something changes the definition. When telescopes first captured it in detail, what stood out wasn't a dramatic shape or a swirl of bright star-forming clumps, but the sheer area of sky it covered, even from such an enormous distance. It's located around 1 billion light-years away, sitting at the dense centre of Arbald 2029, a huge cluster of galaxies bound together by gravity. Clusters like this are some of the largest structures held together in the universe. Hundreds or even thousands of galaxies drift within them, influenced by the collective pull of dark matter, hot gas, and countless stars. And right at the centre sits the largest member, often far bigger than anything else around it. IC 1101 fills that role in this cluster. To get a sense of its size, imagine placing the Milky Way inside it. Our galaxy, with its long familiar disk shape and its hundreds of billions of stars, would sit comfortably within just a small section of IC 1101's width. In fact, you could place the Milky Way there several times over, and there would still be room left around it. IC 1101 spans around 6 million light-years across. Even saying that slowly doesn't completely help. A light-year itself is a distance almost too big to visualize. It's the distance light travels in a year, and light moves at nearly 300,000 kilometers every second. Multiply that by 6 million, and you get a sense of how far one side of this galaxy is from the other. Yet when astronomers study it, they're not just looking at something vast. They're looking at a structure shaped by countless interactions that happened across billions of years. Standing at some imaginary point near its outer edges, if you could do such a thing, you wouldn't immediately be aware of its enormous size. The stars around you would be spaced far apart as they are in any galaxy. If you stretched your arms as wide as they could go, you wouldn't come close to touching another star. Even a spaceship travelling extremely fast would need years to reach the nearest one. Space inside galaxies always feels empty when you imagine being in it. But what makes IC 1101 astounding isn't the density of its stars. It's the amount of space it fills and the number of stars it contains spread across that space. Estimates suggest it might hold around 100 trillion stars. That's a number hard to compare with anything familiar. The Milky Way has a few 100 billion stars. IC1101 has hundreds of times more. Because it contains so many old stars, its glow leans toward yellow and orange. Younger galaxies, especially smaller ones still forming stars, often look bluish because young, massive stars shine brightly before they burn through their fuel. IC1101, on the other hand, seems quiet, calmer. Its population of young stars is small compared with its enormous numbers of older ones. When galaxies merge repeatedly over long stretches of time, they often lose much of the cold gas needed to keep forming new stars, leaving behind a population that grows older and older. IC1101's light carries that story. When you picture its glow, you're seeing the combined light of trillions upon trillions of aging stars, each one tiny in comparison to the galaxy as a whole, but adding to a soft and steady brightness when viewed from afar. Because it sits at the centre of a cluster, IC1101 isn't isolated. It's surrounded by a vast halo of dark matter, unseen yet deeply influential. The galaxies orbiting within the cluster do not move through empty space in a simple way. They are guided by the gravitational shape created by dark matter, hot gas, the mass of all the stars, and the enormous central galaxy itself. When you imagine meeting IC1101, it helps to think not just of a single galaxy, but of its environment, an entire region shaped by its presence. If you could drift near its outskirts, the faint light of its stars would blend into the glow of hot gas filling the cluster, gas heated to millions of degrees and visible only in X-ray wavelengths. That gas surrounds the galaxy like a thin, invisible fog, not dense enough to breathe or touch, but dense enough to shine when observed with the right instruments. From a human perspective, meeting IC1101 isn't just noticing its size, it's noticing how it changes your sense of scale. Galaxies like the Milky Way feel enormous when you think of them alone. They contain enough stars to fill the night sky for countless generations, but standing them next to IC1101 feels a little like placing a single tree beside an entire forest. The structure at the centre of Abell 2029 isn't simply large, it's something that seems to stretch the limits of what galaxies can become. Astronomers often talk about limits to galaxy formation, about how matter interacts, how long star-forming gas survives, and how collisions change shapes over time. IC1101 seems to have taken all of those processes and continued them to an extreme, producing something bigger than almost any model predicts naturally. Meeting it also means noticing its shape. Unlike spirals, which have clear arms and central bulges, galaxies like IC1101 are elliptical. Their structure is smoother, rounder, almost like a glowing cloud when photographed. But that doesn't mean they lack complexity. The stars inside them have a variety of orbits, some long and looping, others tight and fast, all shaped by gravity's pull in a way that forms a balanced, stable structure. When astronomers look closely, they sometimes find faint shells or ripples near the edges, signs of past mergers still imprinted in the distribution of stars. IC1101's sheer size suggests it has undergone many such mergers. Each one leaves a small signature, a trace of the shape the smaller galaxy once held, stretched and blended into the larger system over time. The central region is expected to be extremely bright. Many large elliptical galaxies have cores where the density of stars rises sharply, forming a crowded environment shaped by the presence of a supermassive black hole. In the case of IC1101, the central black hole could be so massive that its gravitational influence extends across distances that are nearly impossible to compare with anything familiar. Stars near the centre would move in complex patterns, influenced both by the combined gravity of the surrounding stars and the deep gravitational well created by the black hole. Observing that region directly is difficult because distance dims everything, but models and comparisons with other massive galaxies give us a strong sense of what's happening there. Another thing that stands out when you think about meeting IC Alarmtosun is how long it has existed in a universe that has changed dramatically over time. The stars inside it formed during different eras. Some are nearly as old as the universe itself. Others formed during mergers long after the galaxy cluster took shape. If you looked closely, you'd see subtle differences in their ages, their brightness, and their compositions. Stars formed early in the universe often contain far fewer heavy elements than stars formed later. That's because heavy elements build up over time as generations of stars live and die. IC 1101 carries within it a record of that progression. Every merger brings in stars with their own histories, and every region likely holds clues about when those stars formed. Meeting IC 1101 for the first time also means noticing what isn't there. You won't find sprawling bands of gas like those in spiral galaxies. You won't see crisp patterns or bright pockets of new star formation scattered across its surface. Instead, you find a galaxy that seems to favour age over youth. That lack of new star-forming gas is partly because many mergers strip gas away. When galaxies collide, gas tends to get heated, stirred up, or driven out of the galaxy entirely by energetic processes. Much of it ends up as part of the large halo of hot gas filling the cluster, rather than remaining inside the galaxy to form new stars. Over time, that lack of available gas means the galaxy grows older without replenishing itself with many younger stars. But even without new stars, IC 1101 remains active in a sense. The interactions between stars, gravity, dark matter, and the motions of galaxies in the cluster create a dynamic environment. The central supermassive black hole may still be pulling in material occasionally, heating surrounding gas or sending out energetic jets during certain phases. Even if those events happened long ago, the signatures can linger in the distribution of hot gas or in the motions of stars. There's depth to this galaxy that only becomes clearer the longer you imagine being near it. At first glance it looks uniform, but over time more details emerge. To meet IC 1101 is also to acknowledge that our ability to see it is limited by the distance. The light reaching us left the galaxy around 1 billion years ago. The structure we observe now is really a picture of its past, not its current state. Even something this enormous doesn't remain unchanged when you consider scales of that length. In the time since the light began its journey toward Earth, more galaxies in the cluster may have drifted inward. Some may have merged with IC 1101. Others might be stretched by tidal forces, leaving long trails of stars behind them. The galaxy we see is a snapshot, but the real object continues to grow and evolve. When you allow the scale, age, and complexity of IC 1101 to settle into your thoughts, there's a gentle sense of perspective that comes with it. Not a dramatic feeling, not a sudden rush of awe, but a slow realization that the universe builds structures of astonishing size through very ordinary processes repeated countless times. Gravity pulls, stars drift, galaxies interact. Over billions of years, these interactions create something that stretches our understanding of what a galaxy can be. Meeting IC 1101 isn't just noticing its scale, it's noticing the patience of the universe, as it allows one structure to grow larger than almost any other we've observed. To understand how something as enormous as IC 1101 comes into being, it helps to take a slow breath and imagine the early universe not as a place filled with fully formed galaxies, but as a place where everything was still settling into roles that would only become clear long after billions of years passed. Galaxies as large as IC 1101 aren't created in a sudden burst or a single dramatic event. They're the result of a steady accumulation of smaller pieces, each one shaped by time, gravity, temperature, motion, and countless quiet interactions between matter. Nothing about the process is rushed. If anything, it happens with the kind of patience that makes even the oldest human civilizations feel brief. The birth of a cosmic giant is a long, gradual unfolding of events that extend far beyond our ability to witness directly. In the beginning, the universe was much denser than it is now. After the Big Bang, matter wasn't evenly spread out. There were small differences in density, slight variations that would eventually shape the entire cosmic landscape. Where matter was just a little thicker, gravity tugged more strongly. Over time, those regions pulled in surrounding material and became the seeds of galaxy clusters. Within those clusters, some areas gathered more matter than others. The centres of these growing structures became natural gathering points, places where gas, dust and dark matter slowly collected into the first recognisable galaxies. IC 1101 didn't appear fully formed. It began as one of these early concentrations of matter, gradually growing more massive as the young universe expanded and cooled. During those early stages, gas flowed into the central regions of clusters, cooling and forming stars. The first stars were enormous compared with the ones we see forming today. They burned quickly and brightly, using their fuel in a short span before collapsing in powerful explosions that enriched the surrounding gas with heavier elements. That enriched gas helped form the next generations of stars. Each time this cycle repeated, the material in the region became more complex. This early period of star formation was intense, producing bright bursts of new stars that lit up the young galaxies. But even at that stage, gravity was already shaping the future path IC 1101 would follow. Larger collections of matter grew faster than smaller ones, drawing in their neighbours and forming the structures that would become the central galaxies of clusters. Over hundreds of millions of years, the early galaxy that would become IC 1101 began merging with others nearby. These early mergers were smaller, involving young galaxies still filled with gas. Every time two galaxies combined, their gas clouds collided, slowed and collected, triggering waves of new star formation. In those early epochs, IC 1101 would have looked very different from its current form. Instead of the vast, smooth old structure we see today, it was more chaotic. Its shape might have been irregular. Star formation would have created bright blue patches scattered throughout. There would have been dense clouds, regions where dust blocked light, and areas where stars were forming so rapidly that they produced intense radiation. The growth of the early structure didn't happen in isolation. Everything took place within the larger environment of the cluster. Galaxy clusters are places where gravitational interactions happen, often compared with quieter regions of the universe. Galaxies orbit the centre of the cluster much like planets orbit stars, though the motions are far more complex. Their paths are shaped by the gravity of dark matter, the hot gas filling the cluster, and the pull of the most massive galaxies within it. Because IC 1101 formed near the centre of Abell 2029's gravitational well, it naturally encountered more neighbouring galaxies over time. Every galaxy nearby was slowly being guided toward it, even if the paths were long and winding. As the universe aged, the nature of the mergers changed. Early on, galaxies merged while still filled with gas, producing bursts of new stars. But as time passed, many galaxies used up their gas or lost it to the hot environment of the cluster. When gas is heated to millions of degrees, it cannot easily cool and condense into new stars. In galaxy clusters, a lot of gas remains trapped in this hot state, glowing in X-ray wavelengths but not forming many new stars. This means that later mergers involved galaxies that contained mostly older stars and very little gas. These dry mergers didn't spark new waves of star formation. Instead, they simply added stars to the growing mass of IC 1101. With each merger, the galaxy grew larger, rounder and smoother. The distinct shapes of the smaller galaxies blurred into the main structure. The process was gradual. It wasn't like watching two objects collide directly. Galaxies often spiral around one another before they merge. They pass close, swing away, slow down and get pulled back inward, repeating that motion until the final coalescence. Each pass distorts their shapes, stretching them through tidal forces and leaving behind long streams of stars. These streams can loop around for hundreds of thousands of light years before blending into the main galaxy. If you could see IC 1101 in enough detail, you might find faint traces of those ancient events, like delicate smudges along its outer regions. They wouldn't be obvious. They would appear almost like slight irregularities in how the starlight is distributed. But they would be evidence of the galaxy's history, each one a remnant of another galaxy that drifted too close long ago. During this long period of mergers, the central black hole of IC 1101 also grew. Supermassive black holes grow not only by absorbing gas that falls into their centres, but also by merging with other black holes. When two galaxies merge, their central black holes begin a slow dance of their own. They spiral toward each other, surrounded by the dense stars at the core of the merged galaxy. Over time they draw closer, eventually combining into a single, more massive black hole. These events release powerful gravitational waves, ripples in space-time that spread outward across the universe. The merger of central black holes is one of the quiet but profound steps in forming a giant galaxy. By the time IC 1101 reached the size we observe today, its central black hole would have grown enormously, influencing the motion of stars within a large region. As the galaxy grew, it also began to shape its surroundings. Massive galaxies at the centres of clusters have a strong influence on the distribution of hot gas. Sometimes the activity around their central black holes pushes gas outward, carving out bubbles or cavities in the hot medium. These cavities can persist for millions of years before the surrounding gas flows back in. Although we can't observe IC 1101's centre clearly enough to see these features directly, other central cluster galaxies show them, and IC 1101 likely behaves in similar ways. This interaction between the black hole and the cluster environment helps regulate the amount of cool gas available for new star formation. When the black hole heats the surrounding gas, it slows or stops the cooling that would otherwise allow gas to fall inward and create new stars. Over billions of years, this effect contributes to the galaxy's aging population. One of the most important aspects of IC 1101's growth is the role of dark matter. Most of the mass in galaxies and clusters is not in stars or gas, but in dark matter, an invisible form of matter that interacts through gravity but not through light. In the early universe, dark matter formed the scaffolding on which galaxies grew. Without it, regular matter would not have been able to gather into dense enough regions to form stars or galaxies. IC 1101 sits within a massive halo of dark matter, much larger than the visible galaxy itself. This halo helped guide the early stages of its growth and continues to influence its shape and size. As other galaxies drifted through the cluster, the gravitational pull of IC 1101's halo helped capture them, drawing them into paths that eventually ended in mergers. The halo may extend far beyond the galaxy's stars, perhaps 10 times farther, forming an enormous invisible structure that binds the entire system together. As time moved forward, the pace of galaxy mergers slowed. The universe expanded, and galaxies in the outer regions of clusters moved farther apart. But near the centre, where IC 1101 sits, mergers continued for much longer. The gravitational influence there is so strong that even distant galaxies feel its pull. Over billions of years, it accumulated stars from every direction. The process was never rushed. It was steady, shaped by the simple rule that gravity brings things together. There were no dramatic turning points, no single moment when IC 1101 suddenly became enormous. It grew step by step, slowly taking in the stars and structures of its neighbours, smoothing out its shape and expanding its reach. By the time the galaxy reached the size we observe today, the universe had changed dramatically. Star formation across the cosmos had slowed. Many galaxies had aged, clusters had matured. IC 1101 had become not just a member of a cluster, but the anchor holding the core of that cluster together. It had grown through a combination of early rapid star formation, steady mergers with smaller galaxies, and the long-term influence of dark matter and gravity. Its size is a record of all those processes acting together for an astonishing length of time. Even now, the growth hasn't fully stopped. The cluster around it continues to evolve. Some galaxies still drift inward on slow, looping paths. They may not merge soon, but given enough time, they will. IC 1101 will continue to collect stars, expand and change its shape slightly as new material blends into the existing structure. The galaxy's story is ongoing, with each new interaction adding to its history. Nothing about its growth is rushed or forced. It unfolds the way the universe tends to do everything on large scales, gradually, steadily, and with a kind of quiet consistency that allows structures like this to form over billions of years. When two galaxies approach each other across the long stretches of a cluster, it's easy to imagine the moment as something violent, as if stars slam together and systems collapse in bursts of light. The reality is almost the opposite. Galactic mergers unfold with a slowness that makes even the longest human timeframes feel brief. They are gradual interactions shaped by gravity and motions that stretch across hundreds of millions of years. Calling it an art isn't exaggeration. There's a certain quiet structure to how galaxies blend. A combination of stretching, drifting, and reforming that eventually leaves behind a single, larger galaxy with traits inherited from both its predecessors. When thinking about how IC 1101 reached its extraordinary size, these mergers are at the centre of the story. To appreciate what actually happens when galaxies merge, picture two objects approaching each other, not like cars on a highway, but like clouds moving through a calm sky. The stars inside them are so far apart that direct collisions are extremely rare. Even in the densest regions of a galaxy, stars are separated by distances so large that they might as well be entirely isolated. If the Sun were the size of a grain of sand, the nearest star would still be far away on the scale of a football field. That emptiness means that when two galaxies come together, their stars simply glide past one another. The path each star takes is shaped by gravity, but rarely does one star hit another. Instead, the entire collection of stars shifts and stretches, as if the galaxies were passing through each other like overlapping swarms of points of light. The real interactions happen between gravity, gas, and motion. Each galaxy has a gravitational field shaped by its stars, gas, and dark matter. When two galaxies come close, these fields begin to tug at each other. The edges stretch first. Stars that were once in stable orbits begin to drift outward, drawn along long arcs that form the tidal tails seen in many merging galaxies. These tails can be enormous, extending hundreds of thousands of light years from the main bodies. They aren't permanent features. Over time, they fall back inward or disperse. But while they exist, they show clearly that gravity is pulling each galaxy into a new shape. The gas inside galaxies behaves differently from the stars. Stars move freely in their orbits, but gas clouds are more like soft structures. When two galaxies collide, gas clouds can slow each other down, lose momentum, or compress. That compression often produces bursts of star formation. In the early universe, when galaxies contained more cold gas, mergers could light up parts of the sky with new stars forming from the compressed material. Many of the bright blue regions visible in images of interacting galaxies come from this process. But in a place like Able 2029, where IC 1101 sits, much of the gas is heated by the surrounding cluster environment. Hot gas doesn't condense as easily. It remains suspended in the intracluster medium, glowing faintly in X-ray wavelengths but not forming many stars. As a result, the mergers that helped build IC 1101 later in its life were quieter, less dramatic, and focused mainly on adding stars rather than creating new ones. When two galaxies first begin interacting, the process can take an incredibly long time. They might pass close to one another and then swing apart again, only to return after millions of years for another close pass. Each time they approach, their shapes distort a little more. Some stars are flung outward into long arcs, others fall inward toward the densest regions. Gas clouds collide, slow down, and shift. The dark matter halos around each galaxy also interact. Because dark matter extends far beyond the visible edges of galaxies, these halos often overlap long before the visible regions do. Their gravity helps guide the final stages of the merger. Eventually, after enough time has passed, the galaxies lose so much energy in their motions that they can no longer pull away from each other. Their orbits decay. The two systems sink toward a shared centre. When they finally combine, their cores merge, their stars mix, and a new galaxy takes shape. It's not an instant change. The combined structure continues to adjust for a long time. Stars settle into new orbits. Gas moves into new patterns. The black holes at the centres of the original galaxies slowly fall toward each other. When they merge, they release gravitational waves, adding another subtle step in the long sequence of events. In the case of IC 1101, this process happened over and over again. It wasn't one merger or even a handful. It likely absorbed dozens or possibly hundreds of galaxies throughout its history. Some of these were small dwarf galaxies, adding only a small amount of mass. Others were larger, perhaps similar to or even greater than the Milky Way. Each event added to the size and complexity of IC 1101. But the more often mergers happened, the smoother the galaxy became. The distinct shapes of the smaller galaxies blended into the larger one. Tidal tails faded, streams of stars dispersed. The result was the enormous elliptical structure we see today. When imagining these interactions, it helps not to picture abrupt collisions, but long, slow encounters where the shapes of galaxies shift gradually. Stars drift in huge arcs, following the combined gravitational pull of the merging systems. These arcs can be beautiful when seen through telescopes. Some look like narrow trails. Others form broad, curving fans of light. They show the path of stars as they were drawn away from their original galaxies. And although they seem delicate, these structures represent enormous numbers of stars moving through space in ways shaped by events that happen millions of years apart. The central region of a merging system is particularly interesting. As galaxies merge, their most densely packed areas, their cores, move toward each other. The stars in these cores are often old and tightly bound by gravity. When two cores approach, their stars interact through gravitational scattering. Some stars may be flung outward into the main body of the combined galaxy. Others settle into new orbits near the centre. The details depend on the mass, shape, and speed of the merging galaxies. But the general pattern is similar across many mergers. Over time, the centre becomes a dense region, often more compact than either original core. In massive elliptical galaxies like IC 1101, this region can be particularly bright and crowded. When the black holes from two merging galaxies meet, they form what is known as a binary system. First, they orbit each other within the dense core. Over time, interactions with surrounding stars drain energy from the orbit, bringing the two black holes closer. When they finally merge, they release gravitational waves strong enough to ripple through space-time. These events are powerful, but not something that can be easily observed for galaxies at the distance of IC 1101. Still, the process plays a key role in shaping the final structure of a galaxy's core. After the black holes merge, the newly formed larger black hole sits at the centre, influencing the region around it for long periods. Not every merger contributes equally. Early mergers, when galaxies still contained cold gas, played a large role in the initial growth of IC 1101. The gas allowed for new star formation, increasing the number of stars rapidly. Later mergers, involving galaxies with less gas, contributed mainly by adding stars. These later events helped expand the size of the galaxy more than they increased its brightness. That's why giant elliptical galaxies often look extended and faint in their outer regions. The stars there are relics of many past mergers, gradually pulled outward by tidal forces and spread into a vast, diffuse halo. Some mergers leave behind visible marks for billions of years. For example, if a smaller galaxy enters on an angled path, the tidal forces might stretch its stars into a loop. These loops can wrap around the galaxy multiple times. If we had a perfect view of IC 1101, it's possible we would see faint loops or shells marking where older galaxies once were. These features are not bright. They're only slightly more concentrated than the rest of the galaxy's light. but they serve as records of past interactions. Each one points to a separate event, a separate galaxy that contributed its stars to the larger structure. In many ways, the process of merging is responsible for the shape of IC 1101. Spiral galaxies like the Milky Way have clear structures with disks and arms because they haven't undergone too many major mergers. A single major merger can destroy a spiral structure entirely. It takes only one large event to turn a spiral into an elliptical. Once that transformation happens, subsequent mergers tend to maintain or enhance the elliptical shape. By the time a galaxy grows to the size of IC 1101, it has undergone enough mergers that any original structure is long gone. What remains is a smooth distribution of stars with no clear patterns or boundaries. The gravitational interactions during mergers also influence how fast stars move. In large elliptical galaxies, stars often travel at high speeds, far faster than stars in spiral galaxies. They move in many directions rather than following organized paths. The motions reflect the combined gravitational history of the galaxy. When IC 1101 absorbed other systems, their stars joined the existing population with their own individual velocities. Over time, the combined motions created a stable but complex balance, where stars fill the galaxy in a wide variety of orbits. The dark matter halos of merging galaxies also combine. Dark matter halos are much larger than the visible galaxies they surround. When two galaxies merge, their halos blend, creating a deeper gravitational well. This deeper well allows the new galaxy to capture more material from its environment. In a cluster where many galaxies are drifting through the same region, a large dark matter halo gives the central galaxy an advantage. It can influence galaxies from greater distances, increasing the likelihood that they will eventually merge. IC 1101 sits inside a massive halo that likely grew through a long sequence of mergers, each adding more dark matter and expanding the halo farther. Another important part of galactic mergers is the way they redistribute angular momentum. In a spiral galaxy, much of the angular momentum is stored in the disk. When two spirals merge, their disks can be disrupted. The angular momentum spreads out, leading to a more spherical or ellipsoidal shape. Over time, as more mergers occur, the angular momentum continues to redistribute. This process helps explain why giant elliptical galaxies rotate slowly compared with spirals. They still rotate, but not in a way that forms a disk. Instead, their rotation is mixed with random motions, producing a rounder shape. What often surprises people learning about galactic mergers is how inevitable they are in certain environments. In a rich cluster like Abell 2029, galaxies are pulled together by the collective gravity of the cluster. Their motions bring them close to one another frequently on cosmic timescales. Even galaxies that start far from the centre may drift inward over billions of years. Once they get close enough, the central galaxy's gravitational pull grows stronger. IC 1101 didn't actively seek out other galaxies. It simply sat at the centre of the cluster, where gravity ensured that other galaxies would eventually approach. As the centuries, millennia, and eons passed, the merging processes shaped IC 1101 into what it is now. Each event added to its mass. Each event erased some part of the incoming galaxy's structure. Each event smoothed the combined system a little more. The result is a galaxy that no longer shows signs of youth, but carries an immense amount of history. The stars inside it tell that story through their ages, motions, and distribution. Thinking about these mergers and the slow, steady way they occur makes it easier to understand how something so enormous could form naturally. Nothing about the process is rushed. Nothing requires sudden change. The universe builds giants like IC 1101 by repeating the same simple interactions over and over again. Gravity draws galaxies together. Their structures blend. Their stars settle. Their halos combine. Over time, the visible galaxy grows larger and smoother, and even now, long after IC 1101 has reached extraordinary size, the environment around it continues to move. Galaxies still drift. the cluster itself still evolves. When exploring why some galaxies grow into giants by absorbing others, it helps to begin with the simple fact that gravity doesn't stop working once galaxies form. It continues shaping their paths, drawing them toward one another over time. In the case of IC 1101, gravity is the central reason it became what it is now. Calling it a cosmic cannibal might sound dramatic, but the reality is far less aggressive. Rather than chasing down nearby galaxies, it simply remains where it is, allowing the environment around it to guide other systems closer. The word devour describes the outcome more than the process. The process itself is slow, quiet, and almost inevitable in the right conditions. The universe doesn't distribute galaxies evenly. They form in clusters, long filaments, and broad sheets of matter that stretch across enormous distances. In regions where matter is especially dense, gravity becomes strong enough to bind hundreds or thousands of galaxies together. These galaxy clusters act like enormous cities in space, with constant motion, interaction, and gradual change. EC 1101 sits at the centre of one of these clusters, Abell 2029. Being at the centre isn't just a simple positional detail, it's the reason this galaxy has grown so large. Everything in the cluster moves around the gravitational centre, and IC 1101 occupies the lowest point in that gravitational landscape. As a result, smaller galaxies naturally drift inward over long periods. When thinking about why galaxies like IC 1101 grow by taking in others, it helps to picture the cluster as a landscape with hills and valleys. The centre of the cluster is the deepest valley. Any galaxy moving through the cluster can lose energy through interactions with the hot gas filling the space, or through gravitational encounters with other galaxies. As a galaxy loses energy, it settles into a lower orbit, gradually spiralling toward the centre. This process is known as dynamical friction. Although the term sounds technical, its effect is straightforward. As galaxies move through the cluster, they experience tiny gravitational pulls from surrounding matter. These small tugs add up, slowing the galaxy's motion over millions or billions of years. The slower a galaxy moves, the more likely it is to fall inward toward the centre. At that central point, IC 1101 remains, waiting without any intention or choice. Its presence makes the central region of the cluster even denser. Every star, every particle of gas, every bit of dark matter adds to its gravitational influence. When a smaller galaxy finally reaches the central region, it doesn't experience a sudden absorption. It simply becomes part of the larger system as its stars spread out into new orbits. The smaller galaxy loses its identity gradually. First, its shape distorts. Then, its stars begin to mix. Over time, the incoming galaxy becomes indistinguishable from the larger one, having contributed its material to the giant growing at the centre. The universe has been doing this since its earliest ages. After the Big Bang, matter gathered into small clumps. Those clumps merged to form larger ones. The process repeated on bigger and bigger scales. Galaxies were built the same way. Small ones combined to form more massive ones. The galaxies at the centres of clusters just happened to grow to sizes far beyond ordinary galaxies because they were positioned where everything around them eventually moved. They didn't choose to consume. They simply existed where consumption was unavoidable. Another reason some galaxies grow by absorbing others is the distribution of mass within clusters. Most of the mass in a galaxy cluster isn't in stars or gas. It's in dark matter. Dark matter forms enormous halos around clusters, extending far beyond what we can see. These halos create the gravitational well that guides the motions of galaxies. Galaxies aren't moving through an empty space. They're moving through a landscape shaped by dark matter. The shape of this landscape determines how galaxies travel over time. Those travelling near the centre lose energy more quickly, while those farther out may take billions of years longer to move inward. Because IC 1101 is located at the deepest part of this gravitational well, it became the natural endpoint for many galaxies within the cluster. As they orbit, their paths shift. Some fall inward quickly, others take longer routes, but once they cross a certain distance, falling inward becomes difficult to avoid. Their dark matter halos interact with the halo of IC 1101. Their stars begin drifting along new orbits. Their gas moves in response to the surrounding hot medium. Over time, the smaller galaxy becomes part of the larger one. Another factor is that galaxy clusters are busy places. Although galaxies are far apart in absolute terms, within a cluster they move through regions where gravitational interactions happen more frequently than in quiet areas of the universe. Every time two galaxies pass near each other, they influence each other's motion. Sometimes these interactions are small, altering only the course slightly. Other times they result in significant changes. Over long enough timescales, these interactions slow down some galaxies more than others, contributing to the likelihood that they will eventually reach the central region. In addition to gravity and dynamical friction, the intracluster medium plays a major role. This medium consists of extremely hot gas spread throughout the cluster. Although the gas is very thin compared to air, a galaxy moving through it experiences resistance, similar to how objects moving through water feel drag. This drag acts over millions of years and reduces the galaxy's momentum. Once again, the galaxy slows down and spirals inward. Smaller galaxies are more affected by this drag than larger ones, because they have less gravitational binding to maintain their speed. Over time, these smaller galaxies lose their gas to the intracluster medium and drift closer to the centre, where they join the growing giant. As IC 1101 continued to grow, each merger added to its gravitational influence. A more massive galaxy can affect nearby systems from greater distances. The larger it became, the easier it was for it to capture passing galaxies. At the earlier stages of the cluster's life, when galaxies were closer together, mergers happened more frequently. But even as the universe expanded and the cluster matured, the core remained a place where galaxies continued to drift inward at a steady pace. It might seem at first as if galaxies only merge when they physically collide, but in reality, the merging process begins long before any direct contact occurs. When two galaxies approach each other, their dark matter halos interact first. These halos extend much farther into space than the visible stars. As soon as the halos begin overlapping, the gravitational forces begin to shape the future interaction. The galaxies start to lose energy through this interaction. Their orbits decay. They begin following curved paths that eventually bring them closer. By the time the visible parts of the galaxies begin to influence each other, the merging process has already entered its later stages. Another interesting part of this process is that not all galaxies falling toward the centre merge immediately. Some orbit the central region for long periods. They pass close, swing around, and then drift outward again, only to return later. Each pass distorts their shape. Stars begin to trail behind them. Gas moves into new patterns. Eventually, the repeated passes weaken the smaller galaxy until it blends into the larger one. These slow, steady orbits contribute to the extended halo of IC 1101, where stars from many smaller galaxies now drift quietly in long paths around the central mass. When considering why some galaxies act as cosmic cannibals, it's helpful to remember that the process is not based on any behaviour or intention. It's a matter of physics. The universe arranges matter according to gravity. Where matter collects, it tends to collect even more over time. The larger structures become even larger. This pattern is seen throughout the cosmic web. Dense regions grow denser, sparse regions grow sparser. In this pattern, cluster centres naturally become the most massive regions. The galaxies sitting at those centres grow by absorbing others, because that is the natural outcome of gravitational systems evolving over billions of years. Another layer to this comes from the fact that galaxies age. Over time, galaxies use up the cold gas that fuels star formation. As they age, they produce fewer new stars. In a cluster environment, this shift happens even faster because hot gas prevents cooling. Galaxies falling toward IC 1101 often arrive already depleted of gas. Thus, when they merge, they contribute almost exclusively older stars. These stars blend smoothly into the existing galaxy. Their gradual addition preserves the elliptical shape and smooth light distribution. Because they don't trigger bursts of new star formation, the mergers don't change the overall colour significantly. Instead, they contribute to the soft, warm glow characteristic of large elliptical galaxies. The growth of IC 1101 through mergers also influences the surrounding cluster. As it becomes more massive, the cluster changes shape. The gravitational centre shifts slightly. The distribution of hot gas changes. Smaller galaxies feel the influence from even farther away. The environment becomes more stable around the centre. Over long timescales, this stability reduces the likelihood of disruptive interactions and makes mergers more orderly. The core becomes a kind of steady gathering place for the stars and systems drawn inward. While thinking about why galaxies devour others, it's important to remember that mergers aren't rare events. They've been part of the cosmic story from the beginning. Our own galaxy will merge with the Andromeda galaxy in several billion years. Smaller galaxies have merged with the Milky Way in the past. The difference with IC 1101 is simply scale. It sits in a place where mergers happen more frequently and where the final structure can grow far larger. By the time we observe it today, IC 1101 has absorbed so many galaxies that its original form is long gone. What remains is a smooth, extended structure created by countless mergers. Each layer of stars, each faint outer region, each subtle change in density reflects the integration of many smaller systems. If you could trace the paths of every star within it, you would find that many once belonged to separate galaxies. But over billions of years, their identities faded. They became part of a new whole, and even now, as the cluster continues to evolve, the process remains active. Galaxies still orbit, some still drift inward. Nothing about the environment stays completely still. When imagining the inner regions of IC 1101, it helps to start by setting aside any expectations drawn from smaller or more familiar galaxies. The core of a galaxy this massive doesn't behave exactly like the centre of the Milky Way, or even the centre of a typical large elliptical galaxy. It's a place where the combined gravity of trillions upon trillions of stars creates an environment that is dense, bright, and shaped by events that have repeated for billions of years. Everything happening there is the result of mergers, star formation long past, black hole growth, and the steady settling of matter into orbits that reflect the enormous scale of the entire system. If someone could stand inside the centre of IC 1101, impossible in practice but useful in thought, the first thing they would notice is how much brighter it would appear compared with many other regions of the galaxy. While the outer areas contain stars spread across immense distances, the core is packed much more tightly. That doesn't mean stars sit right next to each other. Even in dense regions, space remains mostly empty. But compared with the outskirts, the number of stars per volume increases significantly. This concentration produces a steady glow, created by countless individual points of light layered on top of each other, forming a kind of diffuse brightness that comes from the high density of old stars living near the centre. These stars tend to be older because IC 1101's central regions haven't had new, cold gas for star formation in a very long time. As mergers happened and gas was heated or stripped away, the central areas settled into a calm but dense population of aging stars. Many of them have been shining for billions of years. Their colours are typically yellow or reddish, indicating that they've burned through the more energetic phases of their lives. Younger stars, if present at all, would be rare visitors brought in by smaller galaxies that somehow retained a bit of gas. Even then, such stars wouldn't dramatically change the general appearance. The overall glow remains steady and warm, dominated by ancient light. While stars fill the inner region in huge numbers, the way they move introduces another interesting detail. In spiral galaxies like ours, stars follow organised circular paths around the centre. But in the core of IC 1101, the motions are more random. Stars travel in many directions, shaped by the combined gravity of all the stars around them, and the immense gravitational influence of the central black hole. This randomness doesn't mean chaos. It simply reflects the way elliptical galaxies form. After countless mergers, stellar orbits lose the clear structure they once had and become more varied. Over time, this mixture creates a stable but complex pattern where stars move along different paths, each one influenced by the overall gravitational field rather than by a neat rotating disk. The speeds of these stars are remarkable. In massive galaxy cores, stars can move at hundreds of kilometers per second. The gravitational pull in the center of IC 1101 would be strong enough to keep these fast-moving stars bound, but it also means that orbits shift in ways that are hard to predict on small scales. A star might move through the region and experience tiny tugs from many other stars, gradually altering its path. In a system of this scale, these small effects accumulate slowly, producing long-term changes that reflect the galaxy's history. The central black hole is one of the most important features shaping this region. Although astronomers have not yet measured IC 1101's black hole directly, everything we know about massive elliptical galaxies tells us that this black hole must be enormous. In galaxies with similar sizes and brightness, central black holes can reach masses of tens of billions of suns. Some of the largest known black holes, such as those in certain giant elliptical galaxies, even approach 100 billion solar masses. A black hole of that scale influences not just the stars near the very centre, but also shapes the motion of stars far beyond what we might imagine at first. The gravitational reach extends across large distances, affecting orbits and contributing to the overall structure of the core. If someone were to observe this region up close, they wouldn't see a black hole visually. It would be invisible, but they would notice its effects everywhere. Stars would accelerate as they moved nearer to the centre. Gas, if present, would be heated or drawn inward, illuminated by high-energy radiation in cases where small amounts of material fell into the black hole. The region around the black hole might appear slightly different because of this energetic activity, but it wouldn't be dramatic unless a significant amount of gas were falling inward at once. In a gas-poor environment like the centre of IC 1101, the black hole might be relatively quiet much of the time. Quiet doesn't mean inactive. It simply means that the black hole isn't pulling in material at a high rate. Its gravitational influence is still enormous, even when it isn't shining brightly. Surrounding the black hole, the distribution of stars follows a pattern seen in giant elliptical galaxies known as a core profile. Instead of increasing sharply toward the centre, the density of stars may flatten slightly near the very core. This flattening is thought to happen because of interactions involving past black hole mergers. When two galaxies merge, their central black holes eventually meet and form a binary system. As that binary system evolves, it can eject nearby stars through gravitational interactions. These ejected stars move outward, leaving behind a less steep density profile. In the largest galaxies, where many mergers have occurred, this process may repeat several times, carving out a slightly broader core region than expected. If ICL 1101R underwent numerous mergers involving large galaxies, its central region likely bears the imprint of these events. Another layer of complexity comes from the hot gas surrounding the central area. In galaxy clusters, this hot gas fills the space between galaxies and emits X-rays. The central galaxy sits in the middle of this environment. In some clusters, the central region forms a cooling flow, where the gas cools slowly and moves toward the centre. But in many cases, the activity from the central black hole prevents the gas from cooling enough to form new stars. It heats the gas, pushing it outward in powerful but infrequent episodes. These episodes can create cavities or bubbles in the cluster's gas, although detecting such features in ICL 1101 is difficult at its distance. If similar processes occur there, the core may occasionally reshape the surrounding gas, altering the flow of material and influencing how the cluster evolves. Despite the density of stars in the core, the region wouldn't feel crowded on human scales. Even in the densest known star clusters, the distances between stars are enormous compared with anything we experience. If someone were placed inside this region, the sky would appear brighter because more stars would be visible in all directions, but each individual star would still be far away. The sense of scale remains beyond anything familiar. Light would fill the view, not in a blinding way, but as a background filled with more visible points than the night sky on Earth. It would be a subtle reminder of just how many stars exist within the central region of a galaxy this large. The distribution of stars also reflects the ages and histories of the galaxies that merged with IC 1101. Each merger added stars with slightly different compositions and ages. When mergers happened early in the galaxy's history, the stars added were often younger, or part of star-forming regions. When mergers happened later, the stars were generally older. Over time, this built up a population with a wide range of histories but similar ages overall. The core, therefore, becomes a kind of archive. Some stars might be nearly as old as the universe itself, formed in early galaxies that later merged with the growing giant. Others may have formed slightly later during periods when gas was still available. But most of the stars would be ancient, reflecting a long period during which new star formation slowed dramatically. Although gas is scarce in the central region, small amounts can still be present, especially if a merging galaxy retains a bit of cool gas. When such gas reaches the core, it can interact with the hot cluster gas, leading to complex motion and heating. The gas may fall inward toward the black hole, forming a faint disk or being heated into streams that glow at high energies. These processes would be subtle compared with the activity in younger gas-rich galaxies. Still, over long periods, these small inflows can influence the temperature and structure of the surrounding region. The shapes of stellar orbits in the centre can offer clues about the galaxy's past. In some giant elliptical galaxies, the inner orbits show slight preferences in direction, hinting at past mergers or interactions. If we could track the motions of stars inside IC 1101's core, we would likely find patterns reflecting the long sequence of mergers that built the galaxy. Some stars might move in elongated paths, others might move in nearly circular ones. The mix of these orbits contributes to the overall shape. In giant galaxies, this mix leans toward complex, three-dimensional structures with no strong preference for any particular direction. In addition to stars, the central region contains large numbers of stellar remnants. These remnants include white dwarfs, neutron stars, and black holes formed over billions of years. Because massive galaxies contain so many stars, they also contain large populations of these remnants. Many of them quietly orbit in the inner region, contributing mass even though they emit little or no visible light. Their presence affects the gravitational field slightly, but they remain invisible unless they interact with something else. Globular clusters, which are dense groups of ancient stars, also play a role in the galaxy's central environment. Many large galaxies host thousands of globular clusters. Over time, some of these clusters drift inward due to gravitational interactions and dynamical friction. When they reach the centre, they can be disrupted by the dense environment, adding their stars to the core. IC 1101 likely contains an enormous population of globular clusters, many of which have contributed stars to the central region over long periods. These clusters may have originated from the galaxy itself or from the galaxies that merged with it. Each one adds another layer to the complex history recorded in the core. The shape of the central region also reflects the influence of dark matter. While dark matter does not directly interact with stars, its gravitational pull shapes the distribution of matter across the entire galaxy. In the core, the concentration of dark matter is high enough to affect the motion of stars, but not high enough to dominate completely. Most of the mass in the very centre comes from stars and the central black hole, but the dark matter creates the broader gravitational landscape within which the core sits. This landscape determines how stars move at larger distances and how incoming galaxies are affected as they approach. Inside IC 1101, everything moves with a rhythm determined not by noise or vibration but by gravitational balance. Stars orbit, remnants drift, gas heats and cools, The black hole sits at the centre, shaping only the innermost region directly, but influencing the galaxy's evolution indirectly. Nothing appears rushed. Even events that might seem dramatic, like black hole mergers or gas heating episodes, unfold on timescales far longer than any human lifetime. If someone could observe the region continuously over millions of years, they might see subtle changes, but in any short span the core appears steady, holding the weight of an enormous history within a space that always feels calm and unchanging. The more one imagines the inner regions, the clearer it becomes how a galaxy of this scale carries the marks of everything that happened around it. The many mergers that shaped IC 1101 left behind stars moving in different directions, shells of disrupted galaxies, scattered clusters, and a central region smoothed out by countless interactions. Nothing about it is simple, but everything about it fits the natural evolution of a galaxy living at the centre of a massive cluster. Understanding why galaxies like IC 1101 grow by taking in others begins with a closer look at gravity itself, because gravity sits beneath every merger, every drift, and every slow transformation that has shaped this enormous structure. Gravity is often described as a force, but on cosmic scales it behaves more like a field that guides matter into organised patterns. It pulls galaxies together just as it holds stars in place, keeps planets in orbit, and shapes the paths of objects from dust grains to galaxy clusters. When someone imagines a force strong enough to draw entire galaxies together, it's easy to picture something dramatic or forceful. But gravity, even at this scale, works with a kind of steady persistence. It doesn't rush, it doesn't push or slam, it simply pulls objects along paths that arise naturally from their mass and motion. If someone wanted to understand why IC 1101 grew so large, gravity would be the starting point. This galaxy sits at the centre of our Belle 2029, and the centre of a cluster is not a random place. It is the point where the gravitational field reaches its highest concentration. All the matter in the cluster, stars, galaxies, gas, dark matter, shapes the gravitational landscape. That landscape has a natural low point, a region where objects settle over time. IC 1101 occupies that low point. Everything in the cluster orbits around this central region. Some galaxies are on long sweeping paths, others move in tighter loops, but all of them feel the gravitational pull from the centre, and over long enough timescales that pull brings some of them closer. The gentle hunger of gravity in this context isn't a matter of active consumption. Instead, it's the result of physics that applies everywhere in the universe. When an object moves through a gravitational field, its motion can change depending on what it passes near. A galaxy moving through a cluster doesn't simply move in a straight path. It interacts with the gravity of many other objects. These interactions change its speed and direction slightly each time. Most of the time, the change is small, but over billions of years those small changes add up. A galaxy that once orbited far from the centre can drift inward through these tiny adjustments. Eventually it may reach a point where its motion no longer allows it to escape. When that happens, it begins to spiral inward, gradually sinking into the cluster's core. A key process behind this inward drift is something known as dynamical friction. This concept might sound complicated, but its effect is straightforward. When a massive object moves through a region filled with smaller particles, like stars or dark matter, it creates a slight gravitational wake behind it. The particles in that wake get pulled slightly toward the moving object. That pull creates a small drag force. Over time, the drag slows the galaxy down. As its speed decreases, it can no longer maintain its original orbit. It sinks to a lower orbit closer to the centre. For a galaxy cluster where motion is constant and interactions are frequent, dynamical friction plays a major role in guiding galaxies toward the central region, where giants like IC 1101 reside. Another key factor behind galactic consumption comes from the distribution of dark matter. Most of the mass in a galaxy cluster is dark matter, not stars or gas. Dark matter doesn't emit light, but it shapes the gravitational field more strongly than anything else. The dark matter halo around Abell 2029 extends far beyond the visible galaxies. The halo has a shape, a gradient and a depth that determine how galaxies move through it. Galaxies aren't travelling through empty space, they're moving through this vast invisible halo. IC 1101, being at the centre, sits at the deepest part of that halo. Any galaxy that begins drifting inward eventually finds itself unable to escape the gravitational well. Even if it approaches with significant speed, the pull of the halo slows it down. Over time, its motion curves inward, eventually bringing it closer to the central galaxy. As galaxies move inward, they also encounter the intracluster medium. This medium is filled with extremely hot gas that hasn't cooled enough to form stars. The gas is thin, but it exerts a small force on galaxies moving through it. Think of it like a subtle form of drag, much weaker than the resistance a plane experiences in Earth's atmosphere, but strong enough to matter over millions of years. This drag reduces the speed of galaxies. Slower galaxies fall inward more easily. A galaxy that passes through the cluster core several times gradually loses momentum. After long enough, it cannot escape the gravitational field of the central region and becomes part of the larger galaxy. The combination of dynamical friction, dark matter structure, and intracluster drag creates a situation where the central galaxy inevitably grows. Nothing about this process is sudden or forceful. It happens slowly because gravity, on cosmic scales, is weak compared with the other forces in physics. But it has an unlimited range. It acts on everything with mass. Given enough time, weak but continual influence creates dramatic results. IC 1101 didn't need to move or stretch out to meet other galaxies. It simply had to remain where gravity placed it. Every object moving through the cluster responded naturally to the same laws of motion and mass. When smaller galaxies finally reach the central region, another layer of physics takes over. As the incoming galaxy approaches IC 1101, the gravitational fields of the two galaxies begin interacting directly. Stars in the incoming galaxy feel the gravitational pull from IC 1101. Some stars, especially those in the outer regions of the smaller galaxy, may be pulled away early. These stars enter long orbits around the central galaxy. Their original patterns break apart and their new paths reflect the overall gravitational field rather than the structure of the smaller galaxy. This process often begins long before the galaxies merge visibly. In fact, the earliest stages of merging can be identified by faint trails of stars stretching outward from the smaller galaxy, showing where tidal forces have pulled the stars into extended arcs. The inner regions of the smaller galaxy remain intact longer because they're more tightly bound by gravity. But as the merging process continues, tidal forces eventually stretch the entire structure. Depending on the speed, angle, and mass difference between the galaxies, the incoming system may spiral around IC 1101 several times before blending in completely. Each orbit strips more stars, each pass disrupts the shape. Over time, the smaller galaxy dissolves into the larger one, leaving behind no clear boundary or visible remnant except for diffuse streams that eventually fade into the overall glow. Inside IC 1101, the stars that come from incoming galaxies mix with the existing ones. They settle into new orbits determined by the gravitational balance of the combined system. The merging process adds mass and expands the visible extent of the galaxy. As more stars accumulate, the outer regions grow faint but wide, contributing to the immense size that makes IC 1101 one of the largest known galaxies. The physics behind these mergers also involves conservation laws. In any merging system, total energy and momentum must be conserved. When galaxies approach each other, they exchange momentum in complex ways. Some stars gain energy and are flung outward into long orbits. Others lose energy and fall inward. The distribution of stars after a merger reflects these exchanges. Because massive galaxies have deep gravitational wells, many stars from merging galaxies lose enough energy to remain bound to the central system permanently. they become part of the new galaxy, contributing to its size and density. The central black hole plays a smaller but important role in mergers. While it doesn't directly pull in stars from great distances, its presence shapes the innermost region. When two galaxies merge, their central black holes eventually meet. The interactions between these black holes can influence the distribution of stars near the center, creating a slightly flattened core as stars are ejected by gravitational interactions. This effect may not determine whether a galaxy becomes massive, but it helps shape the central structure and contributes to the stable, dense environment characteristic of large elliptical galaxies. Another important physical concept behind galactic consumption is the nature of orbital decay. When a smaller galaxy orbits a larger one, the orbit may shrink over time due to energy loss through gravitational interactions. Dynamical friction is part of this energy loss, but there's also gravitational radiation in the case of black hole binaries, and heating of gas in the case of galaxies with remaining interstellar material. Every mechanism that removes energy from the orbit helps bring the smaller galaxy closer to eventual merger. Over billions of years, these processes guarantee that many galaxies in the cluster eventually reach the center. Galaxies also experience a process called tidal heating when they interact. Tidal heating occurs when gravitational forces from the larger galaxy stretch and compress the incoming one repeatedly as it orbits. Each stretching event transfers energy into the stars of the smaller galaxy. Over time, this added energy erodes the galaxy structure, making it less stable. The stars become more loosely bound. Once they lose enough binding energy, they drift outward, joining the gravitational field of the larger galaxy. This is another way gravity gently consumes incoming systems. It doesn't crush them or collide them violently. It unravels them from the inside out through repeated gravitational interactions. All these processes work together to shape the evolution of cluster centers. Whether someone calls it cannibalism or accumulation or simply growth, the outcome is the same. Galaxies like IC 1101 become enormous because the physics of the cluster environment naturally funnels material inward. Smaller galaxies fall toward the center. They lose energy. They are stretched apart by gravity. Their stars join the central system. The same patterns repeat with each new galaxy that drifts inward, no matter how small or large. Over the lifetime of the cluster, these patterns add up. The central galaxy becomes a record of many separate histories woven into one. Even at the distance where we observe IC 1101, the signs of these processes are visible indirectly. The galaxy's smooth appearance, its extended halo of faint light, its uniform population of older stars, and its central position in the cluster all point to a long history of mergers. The physics behind galactic consumption ensures that this history continues. Even now, galaxies in a Bell 2029 drift along slow orbits. Some of them will inevitably reach the central region eventually. Their stars will scatter and merge into IC 1101. The galaxy will grow slightly larger. Its halo will expand further. Its core will become even more massive. The hunger of gravity here isn't urgent or dramatic, it's patient. A galaxy the size of IC 1101 didn't grow by force. It grew by allowing the laws of motion and mass to guide material toward it. Nothing in the process required anything more than the basic physics that shapes the entire universe. When thinking about what happens to smaller galaxies as they drift toward IC 1101, it helps to begin with a clear sense of the environment they move through. A galaxy cluster isn't an open, empty stretch of space. It's a crowded region on cosmic scales, filled with galaxies of all sizes, streams of dark matter, and large amounts of hot gas. Smaller galaxies don't spend their entire lifetimes in quiet or stable orbits. Instead, they travel along long looping paths shaped by the gravity of the cluster, by interactions with other galaxies, and by friction-like processes that slowly change their motion. As these galaxies move closer to the center over time, their fate becomes tied to the enormous structure waiting there. IC 1101 doesn't actively reach out to pull them in. It simply sits at the point where all these motions naturally lead. Most smaller galaxies begin their journey in the outskirts of the cluster. They may have formed in these regions, or they may have been captured from outside the cluster altogether. In either case, they start far from the central galaxy. At these distances, they feel the cluster's gravity, but not strongly enough to force an immediate inward path. Their motions can extend for billions of years, spending long periods circling the outer parts of the cluster. But even out there, the environment begins to affect them. The cluster is filled with hot gas that creates a slow but steady drag on any galaxy moving through it. This drag isn't enough to stop a galaxy suddenly. Instead, it gradually removes energy from its orbit. Over long periods, the galaxy drifts inward, following a path shaped by the balance between its motion and the gravitational field around it. As the galaxy moves closer to the center, it begins interacting more frequently with other galaxies. These interactions are usually distant. Galaxies don't crash into each other. But even a distant encounter creates a gravitational pull. These small pulls change the smaller galaxy's path slightly. The changes accumulate. The path becomes more irregular. The galaxy might shift from one orbit to another, closer to the center each time. This process happens slowly, but it's consistent enough that many smaller galaxies eventually find themselves near IC 1101's region. By the time a smaller galaxy reaches the central region, it has already lost a significant amount of its original motion. It might also have lost some of its gas, stripped away by the hot intracluster medium. Gas is easier to remove than stars because it isn't as tightly bound by gravity. When gas is stripped away, the smaller galaxy becomes even more vulnerable to the effects of tidal forces. Tidal forces are one of the main reasons smaller galaxies do not remain intact when they get close to giants like IC 1101. These forces arise when different parts of the galaxy experience slightly different gravitational pulls. The side closer to the central galaxy feels a stronger pull than the side farther away. Over time, this stretching effect begins to reshape the smaller galaxy. At first, the tidal forces create subtle distortions. The outer stars drift slightly out of position, forming faint trails. These trails can extend for large distances, tracing arcs that show the future path of the stars. As the galaxy moves deeper into the gravitational field, the stretching becomes stronger. More stars are pulled away. The galaxy becomes elongated, losing its original shape. Spiral arms, if they existed, begin to disperse. The disk, if there was one, starts to warp. Nothing happens quickly. But each pass around the central region strips away more material. Many smaller galaxies follow long, looping orbits around the cluster center. They might pass close to IC 1101 and then swing back out again before returning later. Each pass further erodes their structure. With every encounter, they lose stars, gas, and internal stability. Over many orbits, the galaxy weakens so much that it can no longer hold itself together. It dissolves into the surrounding region, becoming part of the extended halo that surrounds IC 1101. The stars remain, but the boundaries that once defined the smaller galaxy disappear. The galaxy is no longer a separate object. It becomes another layer in the vast accumulation of stars that make IC 1101 so large. Not all galaxies approach IC 1101 from similar distances or in similar conditions. Some are very small to begin with, containing just a few 100 million stars. These dwarf galaxies are easy for tidal forces to disrupt. Once they enter the cluster's core, they may dissolve entirely within only a few orbits. Their stars become unbound quickly, spreading out into faint features that fade over time. These faint, diffuse features form part of what astronomers call intra-cluster light from stars that no longer belong to any single galaxy. IC 1101 contains a huge amount of this light because of the many galaxies it has absorbed over its lifetime. Other galaxies are larger and more resilient. They may resemble the Milky Way or even exceed it in mass. These galaxies survive longer as intact structures. They orbit the central region multiple times before finally merging. Each orbit takes hundreds of millions of years. During these long orbits, the galaxies lose energy through dynamical friction. This friction is stronger for more massive galaxies. As a result, the larger a galaxy is, the more quickly it will lose energy and spiral inward. Eventually, even large galaxies cannot avoid merging with the central giant. When they begin the final stages of the merger, they can cause noticeable changes in the central region. Their stars add to the density. Their dark matter halos blend into the larger halo. Their central black holes begin the long process of moving toward IC 1101's central black hole. During these interactions, the stars of the incoming galaxy do not collide with the stars already in the central galaxy. Space is vast. The distances between stars make collisions extremely unlikely. Instead, the stars move into new orbits shaped by the combined gravitational field of the merged galaxies. Some stars may end up in long looping orbits that take them far into the outer halo. Others may settle into tighter orbits closer to the centre. The final distribution depends on the relative speeds, angles and structures of the merging galaxies. As the smaller galaxy merges, its original shape disappears. If it had spiral arms, they fade. If it had a disk, it becomes distorted and then dissolves. Elliptical galaxies merging into IC 1101 lose their boundaries even faster. They spread their stars across the central region, contributing to a smooth, round distribution. Over time, the central galaxy becomes more and more spherical because the many mergers randomize stellar motion. No single direction dominates. The mixture of motions creates the stable, elliptical shape we observe. Some stars in incoming galaxies gain enough energy during the merging process to escape entirely. These stars are flung out into long trajectories that take them far away from both galaxies. They become part of the broader cluster, drifting through intergalactic space. This phenomenon helps explain why clusters contain stars in their outer regions, with no obvious galaxy around them. These escape stars represent only a small fraction of the total, but they show how energetic the final stages of mergers can be for individual stars. The central black hole of the smaller galaxy has its own path. When the galaxies merge, their black holes begin a slow inward movement. They move through the dense central region, interacting gravitationally with stars and losing energy as they go. Eventually they reach the centre and form a binary system with IC 1101's central black hole. This binary system gradually loses energy, often through interactions with the surrounding stars. Over long periods, the black holes spiral inward until they merge. The final merger releases gravitational waves, contributing to the ongoing evolution of the central region. The fate of the smaller galaxy's dark matter halo is equally important. This halo extends far beyond the visible region of the smaller galaxy. As the galaxy approaches the central region, tidal forces strip away parts of this halo as well. The dark matter becomes part of the larger halo surrounding IC 1101. This process gradually increases the mass of the central halo, making it even more influential. As the halo grows, it affects the paths of other galaxies in the cluster, making future mergers more likely. The cycle reinforces itself over time, allowing IC 1101 to continue growing even into the present era. Throughout this entire process, the smaller galaxy's identity fades. Even large galaxies lose the patterns that once defined them. Their stars become indistinguishable from those already in the central region. Their gas, if any remains, becomes part of the hot intracluster medium, or is heated and dispersed by interactions with the central black hole. Their dark matter becomes part of the larger structure. Only subtle traces of their past existence remain. Sometimes these traces take the form of faint tidal features or shells of stars at specific distances from the centre. These features can persist for billions of years, but eventually they also blend into the background light. If someone were to observe IC 1101 closely, they might find evidence of these past mergers by studying the motions of stars. Some stars may move slightly differently from others, reflecting the paths their original galaxies took when they merged. Others might have slightly different chemical compositions, indicating that they came from galaxies with different star formation histories. These differences don't alter the overall appearance of the central galaxy, but they provide clues to the long sequence of events that shaped it. From the smaller galaxy's perspective, the process is a gradual loss of structure rather than a sudden end. It doesn't vanish instantly. It unravels slowly as gravitational forces stretch and distort it. Its stars are drawn away in long arcs. Its core moves through the central region multiple times, each pass weakening it further. By the time it fully merges, it has been losing stars for millions or billions of years. The final blending is simply the last step in a long path. The fate of smaller galaxies in a cluster like Abell 2029 is tied directly to the cluster's overall evolution. As the cluster grows, more galaxies fall toward the center. The central galaxy becomes larger. Its gravitational reach expands. The environment becomes more stable in some ways and more dynamic in others. Every galaxy that drifts inward contributes to the growth of the central structure. Some contribute only a small amount. Others bring large amounts of stars and dark matter. Over time, these contributions build a galaxy that is far larger than any single galaxy could become through star formation alone. Even at the present time, many galaxies in the cluster continue to orbit. Some may be on paths that will eventually take them toward the center. Others might take longer routes, but the processes that governed the past continue. Smaller galaxies remain bound by the same physics. They continue to lose energy. They continue to be influenced by tidal forces. They continue to drift inward. Their long-term fate remains tied to the central region as the cluster evolves slowly, setting the stage for everything still to come as IC 1101 continues its quiet growth deep within the cluster's gravitational well. When looking at IC 1101 from the perspective of astronomy, one of the most noticeable features is the colour of the light it emits. It doesn't shine with the bright blue patches often seen in young spiral galaxies. It doesn't display the glowing pink regions that mark places where new stars are forming. Instead, it emits a warm, soft glow, dominated by shades of yellow and faint red. This glow is not the sign of a quiet galaxy in the sense of being inactive. Instead, it's the sign of a galaxy where star formation ended long ago, leaving behind a population of aging stars that now define the colour of the entire structure. The colour tells a story about the galaxy's history, its environment, and the processes that shaped it over billions of years. To understand why IC 1101 glows with this older light, it helps to begin with how stars evolve. Stars change colour over their lifetimes. The youngest, hottest stars shine blue or white because their surfaces reach high temperatures. These stars burn through their fuel quickly. They can sometimes live only a few million years before exhausting their hydrogen and moving on to the next stages of their evolution. Slightly older stars with lower surface temperatures emit more yellow and white light. As stars age further and lose heat, their light shifts toward red. By the time a star becomes very old, its colour is dominated by deeper shades of orange and red. In a galaxy filled with many different types of stars, the overall colour depends on how many stars of each type it contains. A galaxy with many young stars will appear bluer. A galaxy dominated by older stars will appear redder. IC 1101 falls firmly into the second category. Its overall colour is shaped by the enormous population of stars that formed billions of years ago. These stars have aged slowly, cooling and reddening over time. Because the galaxy has not formed significant numbers of new stars recently, the older population now defines the visual appearance. This shift toward older stars didn't happen suddenly. It occurred gradually as the environment surrounding IC 1101 changed. In the early universe, galaxies had abundant cold gas, which is the primary ingredient for star formation. Gas clouds collapsed under gravity, forming new stars regularly. IC 1101 likely had an early period when its star formation rate was high. Many galaxies in dense environments experienced these early bursts of activity, but as time went on, the gas supply decreased. mergers with other galaxies changed the structure of the system. Encounters with the hot intracluster medium stripped gas away. The gas that remained was heated beyond the point where it could condense into new stars. This lack of cold gas is one of the most important reasons why IC 1101 appears old. Without cold gas, the galaxy cannot form new stars. Without new stars, the overall population ages steadily. Each generation of stars grows older, and no younger generation appears to replace it. Over billions of years, the stars change colour, and the galaxy's colour changes with them. The warm glow we see today is the natural result of this long period of aging without new star formation. Another factor shaping the colour is the types of stars that are most common in IC 1101. Massive stars, the ones that shine blue and burn through their fuel quickly, are rare even when star formation is active. In galaxies with no active star formation, they disappear completely, since none of them live long enough to remain after billions of years. Medium-sized stars like the Sun live for billions of years and gradually shift toward cooler colours. Smaller stars, which make up the majority of any galaxy, shine with red or orange light for long periods. These lower-mass stars outlive all the others, meaning they eventually dominate the visible glow. Because IC 1101 has a huge number of stars, the overall colour reflects the combined light from all of them. Each star contributes a small amount to the total. Younger stars, if they exist at all, contribute blue or white light. Older stars contribute yellow or red light. But in IC 1101, the older stars vastly outnumber any younger ones. They overwhelm the light of the younger stars, giving the entire galaxy a warm, aged appearance. The environment of a galaxy cluster strengthens this effect. In galaxy clusters, star formation slows earlier than in isolated galaxies. The hot gas between galaxies prevents cold gas from accumulating in large amounts. When galaxies move through this hot medium, their gas is stripped away. Over time, galaxies and clusters become gas-poor, reducing or eliminating their ability to form new stars. IC 1101, being at the centre of a massive cluster, has experienced these effects more strongly than galaxies on the outskirts. Many of the galaxies that merged with IC 1101 were already gas-poor, meaning they contributed mainly older stars rather than fresh gas that could form new ones. The mergers themselves affect the galaxy's colour. When two galaxies merge, the mixing of stars influences the final appearance. If both galaxies are old and gas-poor, the resulting galaxy will be old and gas-poor as well. In IC 1101's case, many of the galaxies it absorbed were already aged systems. They added more old stars to the population. If the mergers had involved gas-rich galaxies, the process might have triggered new star formation. But because the cluster environment stripped gas early and prevented cooling, the mergers did not create new blue star-forming regions. They simply expanded the existing population of older stars. The lack of new star formation also influences how the galaxy changes over time. Without new stars forming, the average age of the population increases steadily. As this happens, the light shifts even further toward the red. If we could have observed IC 1101 billions of years ago, its colour might have been slightly bluer than it is now, reflecting a younger population. But over long cosmic timescales, the cooler, older stars gradually dominate. This shift continues indefinitely, as long as the galaxy remains without a supply of cold gas. Another important detail is how metallicity influences a galaxy's colour. Metallicity, in astronomy, refers to the amount of elements heavier than hydrogen and helium inside stars. Higher metallicity stars tend to be redder because the heavier elements in their atmospheres absorb more blue light. In massive galaxies like IC 1101, metallicity tends to be relatively high. These galaxies formed many stars early, and those stars enriched the gas with heavy elements. When later generations formed, they inherited these heavier elements. Over time, this created a population of stars slightly redder than stars in smaller or less enriched galaxies. The effect is subtle, but contributes to the warm glow. The density of stars also matters. In the central regions of IC 1101, stars are packed more densely than in the outer regions. These densely packed areas contain some of the oldest stars in the galaxy. They have evolved for billions of years, producing stable amounts of warm light. Because the central region contributes significantly to the galaxy's total brightness, the colour of that region affects the overall colour we observe. Even though the outer regions stretch far into space, they are faint. The central regions produce most of the visible light, and their older stars set the tone. If someone were to examine the spectrum of IC 1101, that is the detailed breakdown of its light, they would see clear signs of an old stellar population. Certain features in the spectrum indicate the temperatures and compositions of the stars. These features reveal that the stars are mostly low mass, long-lived, and enriched with heavy elements. They show that the galaxy has not formed significant amounts of new stars for a long time. The small variations in the spectrum reflect the contributions from different types of stars, but the overall pattern matches that of a galaxy dominated by old, evolved stars. Although the galaxy's appearance is dominated by older stars, there may still be occasional pockets of younger stars. These stars could come from small galaxies that retain a bit of gas when they merge. In rare cases, some of that gas may cool enough to form new stars briefly. But such events are uncommon. The harsh environment of the cluster and the strong gravitational influence of the central region make sustained star formation unlikely. Even if a small number of new stars formed, their light would be overshadowed by the enormous population of older stars. Some of the stars contributing to the glow are not just in the galaxy itself, but also in the extended halo surrounding it. This halo is made of stars stripped from smaller galaxies over time. Many of these stars are also old. They drift through the halo in long, slow orbits. Their combined light adds a faint glow that extends far beyond the more concentrated central region. This faint outer halo contributes to the overall size and brightness of IC 1101. But because the stars in this region are also old, the colour remains consistent with the rest of the galaxy. Even the colour gradient of IC 1101 tells a story. In many massive elliptical galaxies, the inner regions are slightly redder than the outer regions. This gradient occurs because the centre formed earlier and contains stars with higher metallicity. The outer regions often include stars from galaxies with different chemical histories and slightly lower metallicity. But the difference is small enough that the overall appearance still reflects a galaxy dominated by older stars. If IC 1101 has such a gradient, it would likely show a similar pattern, with the colour growing slightly cooler at large distances from the centre, but remaining firmly within the range associated with aging stellar populations. The aging of stars in IC 1101 also connects to the way galaxies evolve overall. When galaxies reach a certain size and live in dense environments, they often follow similar evolutionary paths. They lose their cold gas. Their star formation slows or stops. Their colours change as their stars age. Over time, they become dominated by red and yellow light. IC 1101 simply represents this process on a scale much larger than most galaxies. Everything that happens in ordinary elliptical galaxies happens here as well. The difference is the number of stars involved and the amount of time over which the processes have unfolded. In the cluster environment, the glowing population of old stars also affects observations. Because the stars are old and relatively faint compared with the younger blue stars, the outer regions of IC 1101 are difficult to detect. They blend into the background more easily. The faint, smooth light extends for enormous distances, but its brightness is low. This faintness, combined with the warm colour, makes it harder to measure the full extent of the galaxy. Even so, observations reveal that the galaxy stretches far beyond the bright inner core. Everything about its light reflects the accumulated history of star formation, aging, and mergers that took place long before the present era. The ancient light we see today is not only a record of the galaxy's stars, it is also a record of the gravitational events that shaped those stars. Every merger added new stars that were already old. Every tidal disruption spread older stars across the galaxy. Every bit of gas stripped from an incoming galaxy prevented future star formation. Over time, All these processes ensured that the galaxy's colour would shift steadily toward the warm glow we now observe, and even now the change continues slowly. The stars in IC 1101 will keep aging, their light will keep shifting, the overall colour will continue to move slightly toward deeper red tones as the most massive surviving stars complete their life cycles. This steady shift reflects the long ongoing story of a galaxy that has grown through mergers, aged through quiet periods without new star formation, and reached a point where its appearance is shaped entirely by the enduring glow of ancient stars, setting the stage for everything that continues to unfold as the cluster evolves further. Exploring IC 1101 without considering dark matter would leave most of its structure unexplained. The visible stars, gas and dust make up only a small portion of what the galaxy truly contains. The rest exists in a form that cannot be seen directly, does not emit or absorb light, and leaves its mark only through gravity. This invisible component, known as dark matter, provides the framework around which IC 1101 formed, grew, and continued to evolve over billions of years. Without it, the galaxy could not have reached its remarkable size. Its shape, its mergers, its gravitational strength, and even the behaviour of other galaxies around it all depend on the presence of this unseen substance. Understanding how dark matter influences a structure as enormous as IC 1101 helps explain many of the features that define it today. Dark matter does not interact in the ways ordinary matter does. It does not clump into stars. It does not heat up or cool down. It does not radiate energy. Instead, it forms large, diffuse halos that stretch far beyond the visible boundaries of galaxies. These halos act as gravitational wells, pulling in ordinary matter and guiding its motion. In the earlier stages of galaxy formation, dark matter halos formed first, shaped by tiny fluctuations in density shortly after the Big Bang. These halos were the seeds around which the first galaxies began to take shape. Ordinary matter fell into the gravitational wells of these halos, cooled, and eventually formed stars. The shape, size, and mass of each halo determined how large the galaxy inside it could become. In the case of IC 1101, the dark matter halo must be enormous, far larger than the already incredible scale of its visible stars. Observations of similar massive elliptical galaxies and clusters show that their dark matter halos can extend hundreds of thousands of light years beyond the brightest regions. If the visible part of IC 1101 stretches roughly 400,000 light years across, its dark matter halo may extend much farther, possibly more than 1,000,000 light years. This means that anyone observing the galaxy directly would see only a fraction of its full structure. The bulk of its mass remains hidden, shaping everything through gravity rather than light. The size of IC 1101's dark matter halo also explains how the galaxy grew through mergers. When a smaller galaxy drifts into the cluster, its first interaction is not with the visible stars of IC 1101, but with the dark matter halo surrounding it. The halos overlap long before the galaxies appear close together visually. This overlap changes the smaller galaxy's orbit. It begins to lose energy as the two halos interact gravitationally. Even though dark matter does not collide like gas, the gravitational interaction produces effects similar to friction. Over time, the smaller galaxy's motion slows, its orbit decays. The process continues until the smaller galaxy gradually sinks into the larger structure. This long-range influence of dark matter ensures that IC 1101 can draw in galaxies from great distances. The visible part of the galaxy has a strong gravitational pull, but its influence is limited compared with the vast halo of dark matter surrounding it. The halo reaches far into the cluster, affecting galaxies that would otherwise pass by. It creates a region where objects naturally drift inward unless they have extremely high speeds. This extended reach helps explain why the central galaxy of a cluster can grow so large. The dark matter halo pulls in material from across the cluster, not through forceful interaction, but through steady gravitational dependence. Another key role of dark matter involves stabilizing the structure of IC 1101 as it grows. When a galaxy undergoes many mergers, its shape can become disrupted. Stars are pulled in different directions. The gravitational field changes. Without dark matter, these changes might cause chaotic motions that prevent a stable structure from forming. But with a large dark matter halo, the gravitational field remains relatively smooth, even when mergers occur frequently. The halo acts as a stabilizing backdrop. It holds the stars in a broad, consistent distribution. Mergers may change the visible shape slightly, but the underlying gravitational support keeps the system from fragmenting or collapsing into irregular forms. This stabilizing effect also helps explain why large elliptical galaxies have smooth appearances. Their light distributions show gradual changes rather than sharp structures. Spirals have arms and disks because their formation histories differ. Ellipticals lose these features during mergers, but the smooth appearance persists because the dark matter halo maintains a consistent gravitational environment. As stars from incoming galaxies settle into new orbits, they respond to this overall shape. Over long periods, their motion averages out. The galaxy smooths itself naturally, supported by the broader shape of the dark matter halo. Dark matter also influences the motions of stars within the galaxy. When astronomers study large elliptical galaxies, they measure how fast stars move in different regions. These measurements reveal that the stars move faster than they would if visible matter were the only source of gravity. The additional gravity needed to explain these motions comes from dark matter. Although the densest part of the galaxy's mass comes from stars near the centre, the outer regions rely heavily on the halo. Without dark matter, stars in the outskirts of IC 1101 would drift away, unable to remain bound to the galaxy. The halo's gravitational pull ensures that even stars hundreds of thousands of light-years from the centre remain part of the system. In galaxy clusters, dark matter plays an even broader role. Most of the mass in the cluster is also dark matter, not stars or gas. The dark matter forms a cluster-wide halo that extends far beyond any individual galaxy. IC 1101 sits at the centre of this halo. As a result, it experiences the strongest gravitational influence from the cluster's dark matter. This location also contributes to its growth. When other galaxies move through the cluster halo, their paths bend toward the central region. These motions are shaped by the larger dark matter distribution as much as by the visible galaxies. The cluster halo creates a gravitational environment where material is naturally funneled inward. IC 1101, being at the bottom of this gravitational well, becomes the natural point where everything settles over long periods. Without the cluster's dark matter halo, the motions of galaxies would be very different. They might pass through the region and leave again, but because the cluster halo exists, galaxies lose energy gradually and spiral inward. Their long-term fates are determined not just by their own halos, but by the larger structure formed by dark matter across the entire cluster. The blending of halos during mergers also shapes the combined galaxy. When a smaller galaxy merges with IC 1101, its dark matter halo becomes part of the larger halo. This process increases the mass of the final halo, expanding its reach. Over billions of years, after many mergers, the halo surrounding IC 1101 has grown to enormous size. This growth amplifies the gravitational pull, making future mergers even more likely. The cycle reinforces itself. More mass leads to more growth. More growth leads to a larger region of influence. This positive feedback is one of the main reasons the central galaxy in a cluster becomes so massive. Dark matter's influence also helps explain why IC 1101 is not dominated by rotation. Spiral galaxies rotate in organized patterns because they formed in halos that allowed for the stable formation of disks. But in cluster centers where mergers are common, these disks become disrupted. The motions of stars become more random. The dark matter halo supports this random motion by providing a broad gravitational field. Instead of encouraging a disk shape, it supports an elliptical distribution. The stars move in many directions, but the halo keeps their motions bounded. This combination produces the kind of galaxy we see in IC 1101, large, smooth, elongated, and dominated by random stellar orbits. Another interesting influence of dark matter involves the formation of the outer halo of stars. These faint stars, which extend far into space, often originate from merging galaxies, when the smaller galaxy's dark matter halo merges with the larger one. The visible stars from the smaller galaxy spread out gradually. Some of these stars end up on long, slow orbits through the outer regions of IC 1101's halo. Over time, they fill the space uniformly, creating a faint, extended glow. This glow is too dim to see easily, but it contributes significantly to the total size of the galaxy. Without dark matter, these stars would drift away into intergalactic space. The halo keeps them bound, adding to the visible galaxy's enormous scale. Dark matter also shapes how the central black hole interacts with its surroundings. While the black hole influences only the innermost region, the larger gravitational structure provided by dark matter determines how gas, stars, and remnants move on larger scales. Material falling toward the center has to move through the dark matter's gravitational field. The halo indirectly affects how often gas reaches the black hole, how central orbits behave, and how the distribution of stars near the center evolves. Although dark matter does not directly interact with the black hole, its gravitational presence shapes the environment from which the black hole draws material. Another aspect to consider is how dark matter affects the stability of the cluster itself. Without dark matter, a cluster like Able 2029 would not hold together. The visible mass in galaxies and gas is not enough to create the gravitational binding required for a cluster to remain intact. The dark matter halo is the backbone of the cluster. It binds hundreds or thousands of galaxies in a single gravitational structure. IC 1101, sitting at the center, owes its continued growth and stability to the existence of this large halo. Every merger it has experienced was shaped by the same underlying structure. Every galaxy that drifted inward did so because the halo held it within the cluster. Even the temperature of the intra-cluster gas depends on dark matter. This gas is heated by the gravitational forces within the cluster. As material falls into the dark matter halo, it is compressed and heated. The temperature can reach tens of millions of degrees. Gas at these temperatures emits X-rays. Observations of these X-rays provide indirect measurements of the dark matter distribution. The gas responds to the gravitational pull of the halo. When astronomers map the temperature and distribution of hot gas in Able 2029, they can infer where the dark matter is located. The presence of IC 1101 at the center of this gas cloud confirms that the visible galaxy sits at the deepest part of the gravitational well. The steady influence of dark matter ensures that IC 1101 remains a gravitational anchor in its environment. The stars and galaxies moving through the cluster respond to the invisible structure beneath everything. Their paths curve inward, their motions slow, their orbits decay. Over time, more and more material gathers at the center. The dark matter halo guides this process silently, without emitting light, without interacting directly with ordinary matter, and without changing in ways we can see. But its gravitational influence affects everything. If someone could somehow see the dark matter halo surrounding IC 1101, it would not appear as a solid sphere or a clearly defined shape. It would be diffuse, perhaps irregular, extending in a large cloud around the visible galaxy. Its density would be highest in the center and decrease gradually outward. But even in the farthest regions, where the density is low, the gravitational effect would still be strong enough to influence the motions of stars and galaxies. All these interactions, mergers, star motions, gas behavior, structural stability, come from the hidden framework of dark matter. The visible galaxy is only the surface. Beneath that surface lies the structure that allowed IC 1101 to become such a vast and massive system. As the cluster continues its slow evolution, the dark matter halo remains the quiet force guiding every orbit and every future merger, shaping the galaxy's next stages. When trying to understand why galaxies like IC 1101 become so massive, it's easy to focus on the visible stars, the faint outer halo, or the vast spread of dark matter shaping their structure. But deep inside these enormous systems sits another component that plays an essential role in their evolution. This component is the supermassive black hole. Although it cannot be seen directly, and although it occupies only a tiny fraction of the galaxy's total volume, its influence reaches across large distances. It shapes the flow of gas, the behavior of stars, and the long-term structure of the central region. These black holes do not act with the explosive drama that popular imagination sometimes assigns to them. Instead, they work with a kind of quiet persistence, guiding processes that unfold slowly over billions of years. Every large galaxy contains a supermassive black hole at its centre. The Milky Way's black hole has a mass of around 4 million suns. But in galaxies like IC 1101, the central black hole is expected to be far larger. Observations of similar giant elliptical galaxies show that their black holes can reach tens of billions of solar masses. In the most extreme cases, they may approach 100 billion solar masses. These enormous objects grow alongside their galaxies, shaped by the same history of mergers and interactions that build the larger structure. They are not separate from the galaxy's evolution, but deeply connected to it. One of the most important relationships in astronomy is the link between the mass of a galaxy's central black hole and the mass of the galaxy's central bulge or core. This connection, observed in hundreds of galaxies, shows that galaxies with more massive cores have more massive black holes. The pattern holds across different types of galaxies and different environments. For a galaxy as large as IC 1101, this relationship implies an extraordinarily massive black hole. Its core is bright, dense, and extended. The black hole must match that scale. Even though it occupies a tiny region at the centre, it holds enough mass to influence the motions of stars deep into the inner region. The influence of a supermassive black hole depends heavily on distance. Close to the black hole, its gravity dominates everything. Stars, gas, dust, and any other material move according to its pull. But further away, the galaxy's own gravity becomes more important. For a black hole of tens of billions of solar masses, the region where its gravitational influence dominates may extend several thousand light years. This is still a small distance compared with the full size of the galaxy, but it is large enough to shape the structure of the core. The central region of IC 1101 likely contains stars moving at very high speeds because of the black hole. These stars orbit the centre in complex paths shaped by the combined gravity of the black hole and the dense population of stars around them. Even though the black hole does not shine, its presence can be inferred through the motions of these stars. If astronomers could observe the velocities of the stars near the centre, they would find that the motions increase dramatically as they approach the black hole. This pattern is a signature of a massive object hidden within the core. Black holes grow in two main ways. They grow by accreting gas and by merging with other black holes. Both processes played significant roles in the formation of IC 1101's central black hole. In the early universe, when the galaxy still had access to cold gas, the black hole may have fed rapidly. Gas falling into a black hole forms an accretion disk, heating up and producing large amounts of radiation. During these periods, the galaxy may have been much brighter near its centre. The radiation could have pushed away some of the surrounding gas, regulating how much the black hole grew. These active periods come and go. They do not last long compared with the age of the galaxy, but they leave marks on the surrounding region. As the galaxy aged and the environment changed, gas became more scarce. The intracluster medium heated the remaining gas. Mergers disrupted gas flows. The black hole continued to grow, but more slowly. Its primary growth during this later stage likely came from merging with black holes from other galaxies. Each time ICL 1101 absorbed another galaxy, the incoming galaxy brought its own central black hole. These smaller black holes drifted toward the centre of the merged system. influenced by gravitational interactions with the dense stars around them. Over time, they spiraled inward, forming binary or even multiple black hole systems with the main black hole. These black hole mergers unfolded slowly, often over hundreds of millions of years. The black holes orbited each other, losing energy to the surrounding stars or gas. As they spiraled inward, they eventually reached a point where gravitational radiation became the main source of energy loss. At that stage, the black holes merged, releasing gravitational waves that spread through space. The event would not have been visible in light, but it would have produced ripples in the fabric of space-time. After the merger, the newly combined black hole became even more massive, continuing the long process of growth. These mergers may leave behind structural changes in the galaxy's core. When binary black holes interact with stars, they can eject some of those stars from the central region. This ejection creates a slightly flattened or lower density region near the center. Many giant elliptical galaxies show cores with this flattened structure, and IC 1101 likely shows the same feature. The size of such cores can indicate how many black hole mergers have happened. The larger the flattened region, the more mergers may have occurred. In a system as massive as IC 1101, the core may have experienced many such events. Beyond shaping the central region, the black hole influences how gas behaves throughout the inner galaxy. When a black hole accretes gas, it releases energy in the form of radiation and jets. These jets can extend thousands of light years into space, heating the surrounding gas and altering its motion. In galaxy clusters, jets from supermassive black holes play a major role in regulating the temperature of the intracluster medium. They prevent gas from cooling too quickly. If gas cools, it can fall into the center of the cluster and form new stars. But in many clusters, this does not happen. The black hole heats the gas enough to slow or stop this process. This kind of regulation is known as feedback. It is one of the quiet but essential ways black holes shape galaxies. Feedback prevents runaway star formation. It keeps the galaxy's gas supply under control. It maintains the temperature of the surrounding gas. Over long periods, feedback from the black hole may have helped keep IC 1101's appearance stable, preventing large bursts of new star formation. Instead of growing through internal processes, the galaxy grew mainly through mergers. The black hole's influence ensured that the gas could not cool quickly enough to form large new populations of stars. Black hole feedback also helps explain why massive elliptical galaxies like IC 1101 contain mostly old stars. Without feedback, the gas in the cluster might cool and fall into the center, forming new stars. But with feedback, the gas stays hot. It remains suspended in the intra-cluster medium, glowing in X-rays but not forming stars. This environment leaves the galaxy without a steady supply of new stars. Over time, the population ages, and the visible light shifts toward yellow and red tones. The black hole indirectly shapes the color of the galaxy by controlling the flow of gas. Another important influence of the black hole involves shaping the distribution of angular momentum. When galaxies merge, the incoming galaxy often brings stars with specific rotational patterns. As these stars interact with the central region, their motion becomes mixed with the motions of the existing population. The black hole sits at the center, anchoring the region and controlling the dynamics near its immediate surroundings. Although it does not set the rotation of the whole galaxy, it plays a role in stabilizing the central structure and distributing energy among the stars that pass close to it. The presence of a massive black hole also creates a region where stellar orbits can become significantly perturbed. Stars passing close to the black hole may be flung outward into long trajectories or may fall inward and be consumed. These interactions modify the density and distribution of stars near the center. If IC 1101 has a particularly large black hole, this region of strong influence could extend farther than in typical elliptical galaxies. The larger the black hole, the larger the region where its gravitational control dominates. In some galaxies, black holes launch jets that extend far beyond the galaxy itself. These jets are made of charged particles accelerated to near the speed of light. They carve paths through the intra-cluster medium, creating cavities and bubbles that remain for long periods. Although IC11 Neo-1's distance makes it difficult to observe such features directly, similar central galaxies in other clusters show giant bubbles carved by jets from their central black holes. If IC11 behaves like those galaxies, its black hole may have inflated large cavities in the cluster gas at some point in its past. These cavities alter the distribution of gas, influencing how future gas flows into the central region. Even when the black hole is not active, its influence continues. The stars near the center orbit in a gravitational field shaped by both the stellar density and the black hole's mass. Their paths reveal the combined influence. In a galaxy as large as IC1101, these motions likely reflect billions of years of interactions. Stars originally from different galaxies may orbit in different directions. Some may take elongated paths, others may move in nearly circular orbits. The black hole's presence helps maintain order in this complex environment, providing a gravitational anchor for the innermost region. The black hole's quiet architectural role becomes clearer the longer one considers these interactions. It shapes the growth of the galaxy through its influence on gas. It shapes the structure of the core through mergers and feedback. It shapes the motions of stars near the center. It shapes the cluster environment indirectly through jets and heating. Each influence is subtle when considered alone, but over billions of years, the combined effects create patterns that define the visible structure of the entire galaxy. Something else worth noting is that the larger a galaxy becomes, the more important the central black hole seems to be in determining the galaxy's final shape. In smaller galaxies, the black hole is important but not dominant. In the most massive galaxies, the black hole takes on a more significant role. It grows rapidly through mergers, it shapes the density profile of the core, it regulates star formation, its activity influences the surrounding cluster gas. These cumulative roles make the black hole a central component of the galaxy's architecture. Calling it a quiet architect doesn't exaggerate its importance. It captures the idea that the black hole does not act through visible construction, but through gravitational and energetic processes that unfold gradually. IC1101's central black hole has been growing since the earliest days of the galaxy. Every merging galaxy added to its mass directly or indirectly. Every interaction shaped the behavior of gas in the region. Even now, as the cluster continues its slow evolution, the black hole remains at the center, influencing the environment in ways that will continue shaping the galaxy far into the future. To understand IC1101 fully, it helps to look beyond the galaxy itself and consider the larger environment it inhabits. Galaxies do not exist on their own. They form groups, clusters, and superclusters, and the environment around them shapes nearly every part of their evolution. IC1101 is not simply an enormous galaxy. It is the central galaxy of the Abell 2029 cluster, one of the most massive and well-studied galaxy clusters known. This location defines its role, its growth, its history of mergers, and its long-term behavior. Everything about IC1101 becomes easier to explain once the scale of its surroundings is taken into account. A galaxy cluster is a region in the universe where hundreds or thousands of galaxies are bound together by gravity. These galaxies move through a shared gravitational field shaped by dark matter and hot gas that fills the space between them. A cluster is not a quiet or stable environment in the short term. Galaxies move at high speeds, gas clouds stretch across large distances, dark matter forms a vast invisible framework that holds the entire system together. But over long timescales, clusters evolve in relatively predictable ways. They grow by pulling in material from the surrounding regions. They merge with other clusters. Their central areas become denser. The environment inside becomes more intense. IC1101 exists at the point where all of these effects meet. Abell 2029 is an especially massive cluster. Its central region contains a huge amount of hot gas, which emits bright X-rays detectable from great distances. This gas fills the cluster like a diffuse atmosphere, stretching across millions of light years. It is heated to extremely high temperatures by the gravitational forces inside the cluster. As gas falls into the cluster's gravitational well, it compresses and heats up, reaching temperatures of tens of millions of degrees. At these temperatures, the gas becomes fully ionized and emits X-rays continuously. Observing these X-rays allows astronomers to measure the mass of the cluster and map the distribution of dark matter within it. IC 1101 sits at the very center of this massive environment. It occupies the lowest point in the cluster's gravitational well. This location is not accidental. It is the natural consequence of billions of years of evolution. As galaxies move through Abell 2029, their orbits change slowly. Some remain in the outer parts of the cluster for long periods, but others drift inward over time. The central region becomes a gathering point for these galaxies. The result is a dominant central galaxy that grows larger than any other galaxy in the cluster. The central galaxy in a cluster is called a brightest cluster galaxy, or BCG. These galaxies share certain properties regardless of the cluster they inhabit. They are larger than average, they contain older stars, they show smooth elliptical shapes, and they sit directly at the cluster's center. IC 1101 fits this description perfectly. But even among BCGs it is remarkable. Its size exceeds most others by a significant margin. Its faint outer halo stretches farther than almost any galaxy observed. The mass of its central black hole may be among the largest known. These extreme features reflect not only the galaxy's internal processes, but also the history of the cluster around it. In a cluster environment, everything is shaped by gravity on enormous scales. Dark matter dominates the cluster's total mass. Its halo extends beyond the visible galaxies, forming a gravitational field that guides the motions of everything inside. IC 1101 lies at the densest part of this halo. This means the galaxy experiences a constant inflow of material. Smaller galaxies fall toward the center. Gas moves inward until pressure from the cluster environment stabilizes it. Even stars stripped from galaxies drift toward the central region over long periods. The cluster is like a massive basin, and IC 1101 rests at the bottom of that basin. Abell 2029 is not just a cluster, it is part of a larger structure called a supercluster. Superclusters connect many clusters and groups of galaxies into vast filaments that stretch across the universe. These filaments form part of the cosmic web, a network shaped by the distribution of dark matter laid down shortly after the Big Bang. IC 1101's position within this network influences how material flows into Abell 2029. Galaxies and gas move along these filaments toward the cluster, guided by gravity over billions of years. Some of this material eventually becomes part of the cluster. Some of it may even reach the central galaxy itself after long periods of drifting and orbital decay. Understanding how IC 1101 became so large requires looking at how clusters form and grow. Early in the history of the universe, matter was distributed more evenly. Small density fluctuations grew under gravity. Regions with slightly higher density attracted more matter. Over time, these regions collapsed into halos that hosted the first galaxies. These halos merged repeatedly, creating larger and larger structures. Eventually, the largest halos became galaxy clusters. The galaxies inside these clusters followed similar paths. They formed early, interacted frequently, and often merged with each other. Abell 2029 likely went through many such merging events. Smaller clusters may have collided with it. Groups of galaxies may have fallen into it. Each merger increased the overall mass of the cluster. When clusters merge, their central galaxies may also be affected. Sometimes the central galaxies merge with each other. Other times one becomes dominant and grows by absorbing galaxies brought in through the merger. IC 1101's size suggests that it experienced many such events. The more mergers a cluster undergoes, the larger its central galaxy tends to be. The hot gas filling Abell 2029 plays a significant role in the cluster's evolution. Gas is stripped from galaxies as they move through the cluster. This process, known as ram pressure stripping, occurs when a galaxy encounters dense gas in the cluster's core. The gas inside the galaxy can be pushed out by the pressure of the surrounding medium. This leaves the galaxy with less material for star formation. Over time, many galaxies and clusters become gas-poor. Their star formation slows or stops entirely. They become dominated by older stars like ICO 1101 itself. This process not only affects the smaller galaxies but also ensures that ICO 1101 does not receive large amounts of cold gas through mergers. Instead, it receives stars and dark matter from the galaxies it absorbs. The gas from those galaxies becomes part of the intracluster medium, enriching it with heavier elements created in earlier generations of stars. The gas remains hot enough that it does not collapse into new star-forming clouds. This limits the formation of new stars in the central galaxy, reinforcing its status as an old, red-dominated system. Another important aspect of cluster environments is the speed at which galaxies move. In a cluster as massive as a Bell 2029, galaxies can move at thousands of kilometers per second. These high speeds make direct collisions between stars extremely unlikely. They also make mergers between entire galaxies less common in the outer regions of the cluster. When galaxies move too quickly, they pass each other without merging. Instead, they exchange energy and momentum through gravitational interactions. These interactions can alter their paths, but do not necessarily lead to mergers. However, near the center of the cluster, the situation changes. Galaxies moving closer to the center must pass through a region where the gravitational potential is very deep. As they do, they lose energy through processes like dynamical friction. Their orbits decay. They slow down enough that mergers become possible. IC 1101 benefits from this effect. Galaxies that drift toward the center eventually reach speeds low enough that merging becomes likely. Each merger adds mass to IC 1101, contributing to its enormous size. The structure of the cluster also influences the shape of IC 1101. Because the cluster environment is so large and so dominated by dark matter, the stars in IC 1101 experience a gravitational field that changes gradually over distance, but remains consistent over time. This consistent environment helps maintain the smooth, elliptical shape of the galaxy. It supports the faint outer halo that stretches far beyond the bright core. It stabilizes the orbits of stars that would otherwise drift away. Without the cluster's gravitational support, many of these stars might escape into intergalactic space. Even the intra-cluster light, the faint glow between galaxies, is influenced by IC 1101's presence. This light comes from stars stripped from galaxies during interactions. Many of these stars originate from galaxies that passed close to IC 1101. As tidal forces pull stars from smaller galaxies, some become bound to IC 1101, while others end up drifting freely in the cluster. Over billions of years, this process creates a diffuse background of old stars. The presence of this intracluster light indicates the long history of mergers and interactions that shape the central region. IC 1101 sits at the heart of all this activity, absorbing stars and contributing to the environment around it. Abell 2029 is not static. Even now, it may still be growing slowly. Galaxies on the outskirts may be moving inward gradually. Streams of dark matter and gas may be flowing along cosmic filaments toward the cluster. Future mergers may add more material to the cluster and eventually to IC 1101 itself. The evolution of clusters takes place on timescales much longer than human experience. Even if nothing dramatic appears to be happening, the processes continue quietly, shaping the long-term structure of the universe. The way clusters interact with superclusters adds another layer of complexity. Abell 2029 may be part of a larger supercluster that includes other clusters and local structures connected by filaments. Material flows along these filaments toward the densest nodes, which are the clusters themselves. IC 1101, being at the center of one of these nodes, becomes the natural destination for much of this material over long timescales. Its growth is not only the result of local interactions within Abell 2029, but also of larger-scale motions across the cosmic web. Even the location of Abell 2029 within the universe influences IC LENO1. Some regions of the universe contain more clusters than others. These regions form what are known as supercluster complexes. In these dense environments, clusters can interact or move toward each other over billions of years. Abell 2029 may eventually encounter nearby clusters. If this happens, the clusters could merge to form an even larger structure. The central galaxy of the merged cluster would continue to grow through this process. IC 1101 could become even larger as a result, absorbing galaxies brought in through the merger. The temperature and density of the intracluster medium also affect how galaxies evolve. In Abell 2029, the gas is extremely hot and dense near the centre. This gas exerts pressure on galaxies passing through it. It strips gas from them. It slows them down slightly. It influences the distribution of metals, elements heavier than hydrogen and helium within the cluster. These metals come from supernova explosions in the galaxies. As stars die and explode, they release heavy elements into the surrounding gas. Over time, these elements enrich the intracluster medium. The presence of these heavy elements affects how the gas cools and how it interacts with galaxies. All of these processes continue to shape IC 1101's environment indirectly. Even the supermassive black hole at IC 1101's centre contributes to the cluster environment. When the black hole accretes gas, it releases energy that heats the surrounding intracluster medium. This heating can slow the cooling of gas, preventing large amounts of new star formation in the central galaxy. The black hole does not control the entire cluster, but it influences the environment near the centre enough to change the long-term behaviour of gas. This process helps maintain the cluster's overall temperature and prevents the central galaxy from accumulating new cold gas. Although the cluster influences IC 1101 in many ways, the galaxy also influences the cluster. Its gravity helps shape the central potential well. Its stars contribute to the intra-cluster light. Its mergers produce tidal features that enrich the cluster with stars and metals. Its black hole contributes to the heating of the central gas. Together, these interactions show that the relationship between IC 1101 and Abell 2029 is not one-sided. It is a continuous exchange shaped by gravity, motion, and the slow unfolding of cosmic evolution. As time passes, the cluster will continue to evolve. Galaxies will continue to move. Dark matter will continue to guide their paths. The intracluster gas will continue to shift and cool slowly. IC 1101, sitting at the centre, will remain connected to all of these processes. Its future growth, structure, and appearance depend on the cluster around it just as much as they depend on its own internal evolution. The story of IC 1101 and the story of Abell 2029 cannot be separated. They are parts of the same ongoing process, moving forward across vast stretches of time without reaching a stopping point, setting everything in place for the next stages of the cluster's long development. Understanding how IC 1101 became the enormous galaxy we see today requires stepping back to a time when the universe looked very different. The galaxy did not form in isolation. Its size, structure, and stellar population all trace back to conditions that were present only in the early universe. Billions of years have passed since that era, and over those vast stretches of time, many separate events shaped IC 1101 into its current form. By looking at what the universe was like when it was younger, it becomes clearer why a galaxy in a dense environment such as Abell 2029 could grow so massive. Nothing about IC 1101 makes sense without recognizing how time guided its evolution. When the universe was young, it was filled with gas that was denser and more uniformly distributed than it is now. Temperatures were higher, structures were smaller, stars were forming frequently, and galaxies were much more active. In that early era, the seeds for the largest galaxies were already present, although the galaxies themselves had not yet grown to their full size. Dark matter halos formed before visible matter assembled. These halos created gravitational wells, and it was within these wells that the earliest galaxies began to take shape. IC 1101 did not begin as a single, enormous galaxy. Instead, it started as one of many small halos in a region destined to become a galaxy cluster. These halos began attracting gas shortly after the universe cooled enough to allow atoms to form. As gas accumulated, the first stars were created. These early stars were massive, short-lived, and produced heavy elements that enriched the gas around them. Over time, these small galaxies merged with each other, building progressively larger systems. This early build-up is what astronomers refer to as hierarchical growth. Small things merge to form larger things. Larger things merge again to form even larger structures. Hierarchical growth alone does not guarantee the formation of something as large as IC 1101. The galaxy's size reflects not only this early merging activity, but also the environment it lived in. In regions that would later become clusters, density was higher than average, even early on. These dense regions collapsed under their own gravity more quickly. As a result, galaxies in these regions formed earlier, merged more frequently, and built mass faster than galaxies in less dense areas. By the time the universe was only a few billion years old, the central parts of what would become a Belle 2026 were already forming the structures that would later merge into IC 1101. During the first few billion years, galaxies could form stars at extremely high rates because cold gas was abundant. This period is sometimes called the cosmic noon of star formation. For galaxies in dense regions, the rate of star formation could be even higher than average. Gas flowed into the growing protogalaxies along the filaments of the cosmic web. Each new supply of gas provided material for star formation. Massive stars formed and died quickly, enriching the gas with heavier elements. These enriched gas reservoirs later served as the source of new star formation, creating a population of stars that built the core of what would eventually become IC 1101. At this stage, the galaxy did not resemble the smooth, extended elliptical structure we see today. It likely had irregular patches of star-forming regions, thick gas reservoirs, and complex interactions with neighbouring galaxies. Frequent mergers meant that the structure was constantly changing. When two galaxies merged, their stars mixed together, their gas clouds collided, and new bursts of star formation were triggered. Some mergers were small and involved only minor galaxies. Others were major mergers that disrupted the entire system. Over time, these interactions gradually smoothed the structure. The chaotic early stages settled into a more stable arrangement. The black hole that now sits at the centre of IC 1101 also began growing early in the universe's history. When the first stars died, they left behind black holes that served as seeds. Gas falling into these early black holes formed accretion disks that heated up and produced radiation. These early periods of black hole growth may have made the growing galaxy shine brightly in the young universe. As the galaxy merged with others, their black holes merged as well, creating a larger and larger central black hole. This process repeated throughout the early stages of the galaxy's evolution, contributing significantly to the final mass of the central black hole in IC 1101. Another important factor shaping the galaxy's early evolution was the distribution of dark matter. The dark matter halo surrounding IC 1101 grew rapidly during the first several billion years as smaller halos merged into it. Each merger increased the size and reach of the halo. Because dark matter affects how quickly galaxies move and how easily they merge, the growth of the halo influenced the entire structure. In dense regions, halos grew especially fast. The faster the halo grew, the more galaxies it could pull in. The central region of Abell 2029 became a gravitational anchor that drew material inward continuously. During this early period, gas was often funneled into the central region by the structure of the cosmic web. Gas flows along filaments into the densest halos, and the early halo of IC 1101 would have been one of the densest in its region. This meant that even before the galaxy reached its full size, it was experiencing a higher than average flow of gas and smaller galaxies. These flows helped to build up the mass of the galaxy quickly. Although star formation slowed later, it was extremely active during these early times. Many of the old stars seen in IC 1101 today were formed during this early era of intense activity. As the universe expanded, gas supplies gradually thinned out. Galaxies used up their available gas or lost it through interactions. The intracluster medium in Able 2029 began heating during the cluster's early formation. This heating made it more difficult for gas to cool and condense into new stars. IC 1101, being at the centre of the cluster, felt this change early. The hot intracluster medium prevented large amounts of new gas from reaching the galaxy. Star formation slowed as the gas supply dwindled. Eventually, the galaxy stopped forming stars at any significant rate. At this point, most of the galaxy's visible light came from stars that had formed billions of years earlier. But even after star formation slowed, the galaxy continued to grow through mergers. Galaxies already in the cluster moved under the influence of gravity. Over time, many drifted inward. Those that came close enough were absorbed. The stars from these galaxies became part of IC 1101. The dark matter halos blended into the larger halo. The central black hole gained more mass as black holes merged. This long sequence of mergers continued long after the era of rapid star formation had ended. The slower, merger-driven growth shaped the structure of IC 1101. When galaxies merge without much gas, they do not form new stars. Instead, their existing stars mix into the final structure. These mergers tend to produce large, smooth, elliptical galaxies. The repeated mixing of star populations washes out features like disks or spiral arms. Over billions of years, IC 1101 became smoother, more uniform and more extended. Its faint outer halo grew larger and larger as stars from merging galaxies were added in long orbits that stretched far from the centre. The central black hole also evolved during this long sequence of mergers. Early in the universe, black hole growth was driven primarily by gas accretion, but later, when the galaxy had less gas, growth occurred mainly through mergers with black holes from other galaxies. Each merger increased the mass of the central black hole. Each merger also affected the distribution of stars in the core. Over time, the repeated merging of black holes may have created a large, flattened region at the centre of the galaxy. Many giant elliptical galaxies show such cores, and IC 1101 likely has one that reflects its long history of black hole interactions. The chemical composition of the stars in IC 1101 also reflects its early history. Because many of the stars formed when the universe was young and star formation was rapid, they tend to have higher metallicities than stars formed earlier in smaller galaxies. Metals in astronomy refer to any element heavier than hydrogen or helium. These metals are created in stars and released through supernova explosions. In regions with rapid star formation, metals build up quickly. This means the stars in IC 1101 contain a relatively high proportion of these heavier elements. As the galaxy merged with other systems, it gathered stars with different chemical histories. But because the central region formed early, its stars are among the oldest and most enriched in the galaxy. Over long timescales, the structure of the cluster around IC 1101 evolved alongside the galaxy. As Able 2029 grew, it attracted more galaxies. The cluster became larger and more massive. The density of dark matter increased. The intracluster medium heated further. All these changes reinforced the central galaxy's position as the dominant structure. The deeper the gravitational potential well became, the more material flowed toward the centre. The central galaxy became the natural place for this material to accumulate. The process of cluster growth continued throughout billions of years. Even now, Able 2029 may still be attracting new galaxies from surrounding regions. Those galaxies become part of the cluster. Some may eventually merge with IC 1101. The galaxy's slow growth continues even in the present era. Although star formation no longer contributes significantly, mergers remain possible. the galaxy could still absorb smaller systems that drift close enough. The faint outer halo may grow slightly as stars from new mergers join it. When the universe was younger, the types of galaxies that merged with IC 1101 were different from those that merge today. Early mergers often involved gas-rich systems. These mergers triggered star formation and contributed to the growth of the central black hole. Later mergers involved gas-poor galaxies that contributed mainly stars and dark matter. This shift from gas-rich to gas-poor mergers explains why the galaxy's colour changed over time. Early star formation produced bright blue stars that faded as the population aged. Later mergers added older stars, reinforcing the galaxy's overall colour. The timeline of IC 1101's growth reflects broader cosmic trends. The universe expanded, gas cooled, the rate of star formation declined, galaxy clusters grew larger, dark matter halos merged. Over billions of years, these processes shaped the giant galaxy we observe today. The early universe provided the raw materials and conditions for rapid growth. The later universe provided the environment for slow, steady accumulation through mergers. Both stages were necessary. Without the early star formation, the galaxy would lack its dense, enriched core. Without the later mergers, it would lack its enormous size and extended halo. Throughout all these stages, time played the central role. None of the processes were quick. Even the most dramatic events unfolded over millions or billions of years. The creation of a galaxy like IC 1101 required more time than any human experience can relate to. It required the entire history of the universe. Each stage built on the previous one. Each merger contributed to the final structure. Each star that formed in the early universe eventually became part of the faint glow we see today. The galaxy's present state reflects this long accumulation. Its size, its central black hole, its metallicity, its halo, its lack of new star formation, all these features emerged gradually. The early universe provided the environments where rapid growth could occur. The later universe extended those processes slowly. Thinking about IC 1101's future means looking far beyond anything familiar. The galaxy's past and present already stretch across lengths of time that are difficult to imagine, but its future extends even farther. Nothing in the universe remains unchanged. Everything continues to evolve, even structures as massive as galaxy clusters. IC 1101 will keep absorbing material, interacting with its environment, and adjusting to changes in the cluster around it. But the pace of these changes is slow. They unfold over billions of years. They depend on processes that remain constant across cosmic time. By examining these processes carefully, it becomes possible to understand how a galaxy like this might look long after the present era. One of the most important factors in IC 1101's future is the ongoing movement of galaxies within a Bell 2029. Although the cluster appears stable on human timescales, galaxies inside it continue to orbit the centre. Their motions are shaped by dark matter, the intracluster gas, and interactions with other galaxies. Many of these galaxies occupy orbits that take them far from the centre, but over long periods, their paths shift. Dynamical friction slows the largest galaxies. Interactions redistribute energy. Gradually, some of the galaxies that remain at moderate distances will drift inward. This slow inward movement means IC 1101 will continue absorbing new galaxies far into the future. The frequency of mergers will decrease as the number of galaxies that can be absorbed declines. Most of the galaxies located near the centre have already merged with IC 1101 or contributed their stars to the intracluster medium. The remaining galaxies in the cluster's outskirts are spread across large distances. Many move at high speeds. Only some will follow paths leading them toward the centre. As the cluster evolves, the inner region becomes more depleted of independent galaxies. The future of IC 1101's growth depends on the small number of systems still drifting inward. Even though the number of mergers decreases, each one still contributes mass. A single large galaxy merging with IC 1101 in the distant future could add billions of stars to its halo. These stars would settle into new orbits shaped by the combined gravitational field. Some would join the faint outer regions of the galaxy, extending its visible size even farther. Others would settle in the central region, adding to the density. The dark matter halo would expand as well, increasing the gravitational range of the galaxy. This slow accumulation would continue until very few galaxies remain that can be drawn inward. The future of the intracluster medium also affects IC 1101's evolution. The gas in the cluster is extremely hot and held in place by gravity. Over long timescales, this gas will cool slightly, but it will not cool enough to form new stars on a large scale. The central galaxy will remain dominated by old stars. Without new gas inflow, star formation will not resume. The galaxy's colour will continue shifting toward red as its stars age further. The outer halo, already faint, may become fainter still as the stars within it evolve. The overall size of the galaxy might grow, but the visible brightness of the outer regions may decline. The central black hole will also influence the future of the galaxy. Even if gas becomes scarce, black holes can still grow by merging with other black holes. Any galaxy that merges with IC 1101 in the future will bring its own central black hole. These smaller black holes will travel through the dense central region, losing energy through interactions with stars and eventually merging with the main black hole. Each merger increases the mass of the central black hole. Over long enough timescales, the black hole may become one of the most massive in the universe, potentially reaching hundreds of billions of solar masses if enough mergers occur. As the black hole grows, it will continue shaping the environment around it. Even small amounts of gas falling into the black hole can produce energy that influences the surrounding intracluster medium. Jets or radiation from the black hole can heat the gas, preventing it from cooling too rapidly. This feedback mechanism helps maintain the temperature of the central region. Although the overall supply of gas may decline, the black hole's influence remains important. It prevents star formation. It stabilizes the central environment. It ensures that the galaxy remains old and gas poor. On much longer timescales, the stars inside IC 1101 will continue evolving. Massive stars have already completed their life cycles. Medium-sized stars, including those similar to the Sun, will eventually exhaust their hydrogen and evolve into red giants. After shedding their outer layers, they will become white dwarfs. Smaller stars, especially red dwarfs, will live for trillions of years, far longer than the universe's current age. These stars will dominate the distant future of IC 1101. Their faint, steady glow will define the galaxy long after the brighter stars have faded. As the galaxy ages, interactions between stars may gradually change the structure of the central region. Stars may be slowly redistributed through gravitational encounters. Some stars may drift outward, others may move inward. The density profile may shift slightly. But because the galaxy contains so many stars and the gravitational field is smooth, these changes will be gradual and subtle. The overall structure will remain recognizable even as individual stars move across vast distances within it. Another important factor shaping the far future is the motion of the cluster within the cosmic web. Clusters are not stationary. They move through space under the influence of gravity from surrounding structures. Over billions of years, the region containing a Bell 2029 may drift toward other clusters or superclusters. If the universe continues expanding at its current rate, however, distant structures will move away more rapidly. The cluster may become increasingly isolated. As the expansion accelerates, galaxies outside the cluster's gravitational influence will drift out of reach. Only the galaxies already bound to Abell 2029 will remain part of its long-term evolution. This cosmic isolation means that the cluster will no longer receive new material from outside its boundaries. No new galaxies will fall in. No new dark matter will be added. The cluster becomes a closed system. Everything inside is influenced only by the gravity of the cluster, the motions of galaxies, and the slow evolution of stars. IC 1101 will remain at the center of this isolated system. It will continue absorbing the last galaxies drifting inward, but those will be the final mergers. Once they are gone, growth will slow dramatically. Over even longer timescales, the intracluster medium may cool slightly as it radiates energy. But because the gas is held in place by the cluster's gravity, it will not escape. Instead, it will remain as a diffuse, hot environment surrounding the central galaxy. The stars within IC 1101 will continue aging. White dwarfs will cool slowly. Red dwarfs will continue shining faintly. The galaxy's brightness will decrease steadily as the average luminosity of its stars declines. The dark matter halo around IC 1101 will remain, although the visible galaxy may shrink in brightness. The halo ensures that stars remain bound to the galaxy even as the universe expands. But the halo itself will not change dramatically once mergers stop. It will become a static part of the galaxy's structure, supporting the long-term motions of the remaining stars. Another slow process that will influence the galaxy's far future is the gradual evaporation of stars. Over very long timescales, stars in the outer regions of galaxies can gain enough energy through gravitational encounters to escape. This process takes far longer than the current age of the universe, but it becomes noticeable in the distant future. Some stars may drift away into intergalactic space within the cluster. Others may escape the cluster entirely if they reach high enough speeds. The rate of evaporation is extremely low, but over trillions of years it can subtly change the distribution of stars. In the very distant future, when most stars have evolved into white dwarfs or red dwarfs, the galaxy will appear much fainter. But the structure will still exist. The stars will still orbit within the dark matter halo. The intracluster gas will still fill the space between galaxies. The central black hole will remain, continuing to influence its immediate surroundings. IC 1101 will look quieter, dimmer and older, but it will still exist as a coherent structure. If the acceleration of the universe's expansion continues indefinitely, eventually galaxies outside our Belle 2029 will move beyond the observable horizon. The cluster will become one of the few remaining structures visible from within its boundaries. Over incredibly long timescales, each cluster becomes isolated, cut off from the rest of the universe. IC 1101 becomes part of one of the last large structures left behind in a universe where everything else moves out of view. The possibility of cluster mergers in the far future depends on the balance between gravitational attraction and cosmic expansion. If nearby clusters are close enough and moving slowly enough, they may still merge. If not, the expansion will carry them away. In the case of Abell 2029, the cluster may remain isolated. Its future mergers will occur only among the galaxies already bound to it. Inside the cluster, galaxies that still retain some motion toward the centre will continue their inward drift. Their mergers with IC 1101 may be slow but inevitable. Each merger adds material to the central galaxy. If the cluster contains any particularly large galaxies that have not yet merged, these mergers could significantly increase the mass of IC 1101. Depending on the number and size of the remaining galaxies, IC 1101 could grow to an even more remarkable scale. In a distant era, when most stars in the galaxy are faint and old, the central black hole will remain as the most massive and enduring component. Black holes evaporate through a process called Hawking radiation, but the timescale for evaporation of a supermassive black hole is extremely long, far longer than the time it takes for most stars to evolve. Even in a universe trillions of years from now, the black hole at IC 1101's centre would still exist. It would influence the region around it just as it does today. The stars that remain will continue their slow evolution. Some may be captured by the black hole. Others may be perturbed into long orbits by interactions with nearby stars. The motions of stars will remain complex but stable. Even though the galaxy's brightness will fade, the underlying structure will persist. The faint outer halo will become less visible, but the stars within it will continue orbiting, bound by gravity. The galaxy may shrink slightly in visible extent as the faintest stars fade, but the physical structure will remain large. Throughout all these long-term processes, IC 1101 will remain connected to the evolution of Able 2029. The cluster's gravitational well will continue shaping the motions of stars and galaxies. The intra-cluster medium will remain hot. The dark matter halo will continue providing the framework for everything inside. The central galaxy's future is tied directly to the cluster's future. Spending so much time following IC 1101, through its earlier seeds in the young universe, through the long stretches of cluster evolution, and into the far future where only the slowest processes still matter, creates a certain kind of perspective. When looking at a galaxy that large, it becomes easier to recognize how every part of its structure is the result of steady accumulation. Nothing about IC 1101 formed quickly. Nothing happened in abrupt steps. Its entire existence is a continuous process shaped by gravity, motion, temperature, and time. Even the parts that first appear overwhelming begin to feel understandable once the pieces are laid out across the appropriate scale. Seen this way, the galaxy becomes less a mystery and more a reflection of everything that happens when the universe is given enough time to let its rules play out. Every detail about IC 1101 connects to the idea that galaxies respond to their environments. The environment around IC 1101 is not small or simple. It extends across millions of light years, filled with hot gas, fast-moving galaxies, and a massive dark matter halo that defines the motion of everything inside. IC 1101 sits at the centre of all of this, not because it forced its way there, but because that is where gravity naturally guided the material over billions of years. The galaxy did not have to do anything to become the central object. It simply needed to exist in a location where everything else would eventually settle. Tracing that process backward reveals a long path starting in the early universe. At that time, the first stars were forming, the first galaxies were assembling, and the first clusters were beginning to take shape. The region that would become Abell 2029 had slightly more matter than average. That small difference, barely noticeable in the earlier stages, became a defining factor billions of years later. Matter collected more quickly in that region. Halos merged faster. Galaxies formed earlier. By the time the universe reached the period of peak star formation, the building blocks of IC 1101 were already well established. Looking deeper into that early time shows a period when galaxies collided regularly. The collisions were not destructive on a stellar scale, but they did dramatically reshape the galaxies involved. Gas clouds compressed and formed stars. Black holes merged. The structures changed repeatedly. These continuous interactions built the core of what would become IC 1101. That core contains some of the oldest stars in the galaxy. Their age reflects the era in which they formed, a time when star formation rates were high and the universe was much younger. As the universe aged, the environment changed. Gas became harder to accumulate. The intracluster medium heated and expanded. Star formation slowed not only in IC 1101, but across most galaxies in dense clusters. The galaxy entered a new phase of evolution where its growth depended less on new stars and more on mergers. This phase lasted much longer than the earlier one. It shaped the galaxy into a smooth, extended elliptical structure, with a faint outer halo and a dense core. The core itself provides a kind of timeline. Its stars formed early. They evolved over billions of years. Their light shifted from blue to yellow and then toward red. Because no significant star formation occurred later, the light from the core now reflects a population that has aged together. The outer halo contains stars from many different origins. Some formed in galaxies that merged with IC 1101 billions of years after the core began taking shape. Others formed early but were pulled out of smaller galaxies that drifted close to the central region. Their orbits stretch far from the center, giving the galaxy its enormous size. Every one of these stars follows a path defined by the galaxy's dark matter halo. That halo is invisible, but its presence is unmistakable in the motions of stars and galaxies. Without dark matter, IC 1101 could not hold its faint outer regions together. The stars would escape into intergalactic space. Instead, the halo provides a gravitational framework that shapes everything across hundreds of thousands of light years. It is the most stable part of the galaxy. Even if the stars change, even if mergers alter the visible structure, the halo remains. Moving outward from the galaxy into the broader cluster reveals the environment that supported IC 1101's growth. The hot intracluster gas, spread across millions of light years, plays an important role. Its temperature affects how galaxies evolve. Its density influences how easily gas is stripped from galaxies that pass through it. Its metallicity reflects billions of years of star formation and supernova explosions. IC 1101 exists within this environment, affected by it at every stage. The hot gas prevented new star formation in the later phases of the galaxy's evolution. It removed gas from incoming galaxies. It kept the central region in a state where mergers dominated. The cluster's dark matter halo shapes everything at an even larger scale. It keeps galaxies bound to the cluster. It guides their orbits. It slows their inward drift through processes like dynamical friction. Without the cluster halo, many galaxies would not interact with IC 1101. Their paths would carry them away. Instead, the halo ensures that the central region remains the final destination for many galaxies. Over billions of years, this steady flow of galaxies created the enormous system we see today. Even on the smallest scales, the influence of time remains obvious. The white dwarfs scattered throughout IC 1101 represent the final stages of stars that lived billions of years. The red dwarfs represent stars that will continue shining long after larger stars have faded. The remnants of supernovae contribute to the chemical makeup of the intracluster medium. The central black hole holds the memories of a long sequence of mergers with smaller black holes. Every part of the galaxy contains evidence of long-term processes, each shaped by time rather than sudden events. Considering the future of IC 1101 means recognizing that time plays the same role going forward as it did in the past. The cluster will continue to evolve, its galaxies will continue to move, some will drift inward and merge, others will remain on distant orbits that never bring them close enough. The intracluster medium will remain hot, held in place by the cluster's gravity. The central black hole will continue influencing its surroundings. The stars will continue aging. Nothing stops. Everything continues, just at a pace too slow to observe directly. The cluster's long-term isolation plays another important part in its future. As the universe expands faster and faster, galaxies outside gravitationally bound structures will move away beyond any possibility of interaction. Abell 2029 will remain intact, but it will be cut off from new material. This isolation turns the cluster into a closed system. IC 1101 will remain at its centre, absorbing the last galaxies that still move inward. But eventually the supply of new galaxies will decline. When that happens, the galaxy will continue to exist but will grow more slowly. Its structure will remain stable, held together by a combination of dark matter and the gravity of its stars. Because IC 1101 contains so many stars, its brightness will decline slowly rather than abruptly. Different types of stars evolve on different timescales. Some will become red giants, and then white dwarfs. Others will continue burning hydrogen for trillions of years. Over extremely long durations, the galaxy's light will fade, but it will retain its structure. Even if the faint outer regions become harder to distinguish, the stars will remain bound to the galaxy. Looking at these long-term processes together, IC 1101 becomes an example of how galaxies record the history of the universe. It preserves information about the early star-forming era in its central regions. It preserves information about the long phase of mergers in its extended halo. It preserves information about the cluster environment in the distribution of its stars. It preserves information about black hole growth in the structure of its core. Each layer reflects a different part of cosmic history. None of the layers stand alone. They blend into each other, creating a single structure built from countless separate events. Spending time with these details makes the galaxy feel less overwhelming. It stops being an impossibly large system and becomes something understandable step by step. Every part fits into a larger pattern. Every feature has a cause. The more one looks at it, the more natural it seems that a galaxy like IC 1101 would form in a dense cluster environment. The conditions that created it may be extreme, but they follow the same rules that shape ordinary galaxies on much smaller scales. Stepping back from the details adds another layer of clarity. IC 1101 does not exist alone. It is one of many central galaxies and clusters across the universe. Each one reflects its cluster's history. Each follows the same basic path: early star formation, gradual decline, long sequences of mergers, and slow aging. IC 1101 stands out because of its scale, but its story parallels those of other central galaxies. It simply took the same processes further, shaped by a cluster that became larger than most. When imagining drifting away from the galaxy, farther and farther beyond the bright core, beyond the faint halo, past the hot intracluster gas, and into the broader cluster, everything remains connected by the same continuous pull of gravity. The farther the distance, the more the cluster blends into a larger structure. Eventually, the galaxy becomes one part of a broader environment stretching across millions of light years. From there, it becomes clear how the galaxy fits into the cluster and how the cluster fits into the cosmic web. Nothing sits alone. Everything links to the next scale. Moving slowly outward in thought, it becomes easier to see how the galaxy's long history continues shaping its future. Every star still orbits. Every galaxy still moves. Every part of the cluster still responds to the same gravitational field. IC 1101 remains at the center, shaped by what came before and continuing through what comes next, following the steady pull of time that guided it from the beginning.